And welcome to the final of the Brazilian Physicists Tournament. This year we have 4 teams. We have Unicamp, USP, UFMG, and also UFABC. And, well, during the tournament so far, we have only had fights between 2 teams per room. So we only had the presenting team and the opposing team. But now, in the final, we've decided to gather all 4 teams in just one fight. So we're also going to have the reviewer role, and also one of the teams will be the observer. Okay, so we are going to start pretty quickly this time. But first, I would just like to start introducing all the jury members. So I'd like to ask, please, if the jury members would like to identify themselves. Just please go ahead. For example, Matheus Farias, just give a quick introduction.
Hey everyone, my name is Matheus Farias. I'm a PhD student at Harvard, and I study the intersection of computer architecture and machine learning. Good luck for you all. I'm excited to see this physics fight today.
Nice, thank you very much. Now, please, Barbara.
Hi everyone, I'm Barbara. I'm a physics PhD student at Columbia. I work on astronomical instrumentation, and my connection to the IPT, I guess, is for the IYPT because I represented Brazil twice when I was a teenager.
Cool. Okay, now let's see. Oh, we also have Professor Edward.
Hello, everyone. My name is Edward Ferraz. I'm a professor in UFOB, Barreiras, Bahia. I wish the great fight today. Congratulations for teams, and bye-bye.
It's cool because Edward's names allow me to say things like Edward, in proper English, because sometimes I get, I gotta say like Rodrigo or Rodrigo, so yeah, sometimes but Edward, thank you for your name. Now, let's see, we also have Alexandre.
So, good afternoon, my name is Alexandre Rocha. I'm a professor at Instituto de Física Teórica at Unesp, and I work on condensed matter physics. Mostly computational work on nanoscopic systems, optical properties, and electronic properties of materials.
And we also have here Professor Claudio Lenz.
Hello, everybody. I'm Claudio Lenz Caesar, professor at the Federal University of Rio de Janeiro. I work with antimatter, anti-hydrogen, and atoms and molecules and lasers and ions and things like that. And I'm really excited to see this final. It's my second time at BPT, and it's very nice to see the creativity of the groups to tackle the problems. So good luck to everybody.
All right, thank you very much. I think I've already announced everyone. Am I right? I think I'm not missing any of the jury members, I believe. So I believe we can move on then and just ask the teams, the team captains, just to quickly identify their teams. So first off, team of University of São Paulo, could you please just, Lauro, I know you're the captain. Just introduce your team.
Thank you, Matheus. I'm Lauro, the team captain of the team USP, and I'm here with Bruno Siqueira and also with Matheus Teixeira de Souza, which are my colleagues.
All right. Now, similarly, I would like to ask the team from the Federal University of Minas Gerais to the team captain to introduce their team members, please.
Hello, everyone. My name is Bernardo, and today I'm representing the team UFMG with our team members Bianca, Pietra, Felipe, Gabriel, and Renan. It's a pleasure to be here.
All right. Now, similarly, I would also like to ask the team from the team captain from Unicamp to introduce themselves.
Good afternoon, everyone. I'm Leonardo, and I am here with Adriano, Gustavo, Álvaro, João, and Lucas, and we are the team Unica.
Cool. Now, the last team composing this physics fight, the team from the Federal University of ABC. If the team captain could please identify their members.
Hello, everyone. My name is Lucas, and I'm here with Rodrigo, Vinicius, and Leonardo to represent the team of UFABC. It's a pleasure to be here too.
Gustavo, Álvaro, João, and Lucas, and we are the team Unica.
Ooh. Now, the last team composing this physics fight. I'm watching. Sorry, I just put it. Okay. Now everybody present. I was just looking at the broadcast. Okay. So I believe we can give it a start to the physics fights, captain fights. Let's see here. Okay, so can you all see my screen properly?
Yes.
Okay. So just as a reminder, this captain's fight is to decide which team will choose, in which order they will choose, and that can be a little confusing, to present on the physics fight. So for example, the first team can choose if they want to choose first, choose second, or choose third in this first round. And I believe that Henrique could also like correct me if I'm wrong, but the team that comes last in this physics fight, this captain's fight will already be the observer, and then the three other teams will we'll start the physics fight, right?
The captains
they can choose to be observer too.
The observer, the captains can choose the position if we would like to see the observer in the first round, they can.
Okay, cool. So they can do everything. Okay, that's nice then. So it's just a matter of choosing in which order they'll choose. I mean, the last person, the last team to choose won't have a choice, but let's see then. So, well, okay, so here we have gathered once again the teams from University of São Paulo, University of Federal University of Minas Gerais, Unicamp, and UFABC. And I would just like to also again remind the team members from the team captains that will join this captain's fight to write down their answers and then point them to the camera as soon as the clock hits the 3 minutes. So yeah, without further ado, I think we can start. So well, let's see here. Okay. All right, I'm gonna start then. So each of you will have 3 minutes to solve the following problem that I will read, and then further on you have 3 minutes. Just write down your answers. And I believe we can start now. So the problem is donut-shaped planets. The flat Earth hypothesis has been recently rediscussed after centuries. Now, as a next level exaggeration, we could also take into consideration a donut-shaped planet. Also, açaí is a typical Brazilian fruit which is enjoyed in the whole country, but mostly in Pará, its largest producer. Now, suppose that we can build up a donut-shaped planet that is filled with açaí pulp. Assume the donut's inner radius is the moon radius and the outer one is the Earth radius. How much time would it take in years to fill the planet up, assuming the açaí production rate of Pará? You have 3 minutes starting now. We have 40 seconds. Oh, 15 seconds. And that's it. The time's up. So please, I would like the team captains to show their answers on the screen, please. Wait, let me just pin you all because I think it will be easier. I haven't been pinning. Well, in some of you, I cannot see the answer yet. Wait, let me just stop sharing and see the answer here. So USP said 153 years. UFABC said 10 to the 17 years. Unicamp team, I cannot see your answer, but
5,000 years.
Oh, okay, sorry. Okay, thank you. Unicamp, so it's 5 times 10 to the 3 years, and the team from UFMG 1,000 years. So 10 to the 3. So all right. So let's see the answer. So Peraza's production in 2020 was of about 1.5 times 10 to the 9 kilograms. Acai pulp density is mostly composed of water, so it's about 10 to the 3rd kilograms per meter cube. Assuming the donut is a torus, its volume is calculated as this equation here, where you have the inner radius and outer radius that we've commented during in the problem already. So yielding a volume of 6.75 times 10 to the 20 meters cubed. This would correspond to a mass of 6.75 times 10 to the 33 kilos. And so assuming the absolute production rate is that same that we talked about before, over a year, the amount of time that it's needed to fill up the planet will be something like 4.5 times 10 to the 14 years, which is greater than the age of the universe. Oh my God, can you believe that? So, I mean, so unfortunately, we will not see a planet that's shaped as a torus and made of acai, unfortunately. But it would be really interesting.
That would be awesome.
Yeah, right. And I mean, this planet will be like considered Brazil land, I believe, Brazil's land. Well, anyways, so let's look at the answers again. So here I have USP's guess was approximately 10 to the 2nd, 153 years. UFABC team was actually really close with 10 to the 17 years. Unicamp 10 to the 3rd, and UFMG 10 to the 3rd. So I believe in logarithmic scale, of course, UFABC team will be the first one to choose in which position they'll choose. And I believe in the second to choose where to be, I believe it's Unicamp, and then UFMG. And in 4th place, the team from USP. All right, I can also check that. Let's see. Well, moments of tension, but I believe it's correct. So okay. So the first team that can choose where to choose is the team from the Federal University of ABC, and therefore I would like to ask the captain of the UFABC team in which order would they like to choose? Would you like to choose first, second, or third?
We would like to choose third.
All
Can you hear
right.
me?
Yes. So the team from Unicamp, I'd like to ask which position would you like to choose?
Yeah, we'd like to choose first.
Okay, choose first. So now the Bernardo from UFMG, in which position would you like to choose? Second or fourth?
We would like to be the second to choose.
Cool. Thank you. And therefore, Team USP will be the last one to choose. So let me just check here. Let me just project one image to help you out. I believe it will be of great help for the teams as well. All right. So the first team to choose is Unicamp. So I would like to ask Unicamp, in which position would you like to have first?
We would like to start observer. So
Okay. Now the second team, UFMG, you can choose which role would you like to take in the first round?
we would like to be the reporter in the first round.
Okay, thank you very much. Now, UFABC, what would you like to do on the first round?
We would like to be reviewer.
Okay. And now the team from USP, you will be the opponent for Team UFMG then. All right. I think we're all set then. So the first team to report will be UFMG, opposed by team from the University of São Paulo, and the reviewer would be the Federal University of ABC, and observing team will be Unicamp. Then Unicamp will take on a role of reviewer. Then I already confused myself, but you can see the order there, so they'll change. So the first round. Oh, okay. Oh, actually, no. Wait. I was reading this. I was reading this wrongly. Sorry. So the first team to report will be Unicamp. The observing team. No, the first reporter team will be UFMG, and then the opponent will be USP, and the reviewer team would be UFABC, and Unicamp will be the observer. Then Unicamp moves on on the second round as the reporter team, and the opponents will be UFMG, observed by UFABC, and reviewed by USP. So I'm not going to talk about all the roles right now. I'm just giving you an idea of the progression. And sorry, I made that little mistake. I was just doing everything live. Something happened. Okay, so I believe we can already start going. Let's see. Henrique, are we good with the time and everything? Can we proceed? Okay. So the reporter team has 3 minutes to prepare their presentation. So please, UFMG, you have 3 minutes starting now.
Mateus,
yes.
I don't have permission to share.
Oh, okay. Yeah, no, that'll be solved. Okay, so Henrique, please just the permission. And meanwhile,
oh yes, thank you.
all right. So Team UFMG will present droplet sanding fingerprints, and I'll just read the problem statement for everybody.
Just a second. My mouse is not actually working properly.
Okay. No problem.
Is it, just a few questions. Can you hear me properly and see the screen changing properly?
Yes.
Is the cursor visible for you?
Yes, it's also visible. Okay. So let me just read the problem statement. So problem is droplet sanding fingertips. When droplets fall on a surface covered by a layer of sand, interesting patterns are formed. Study the formation process. What parameters of the droplets can be inferred from the resulting crater? That's the problem statement. And yeah.
Okay. I'm ready to start, and let me know when you start the clock, please.
All right. Let me just wrap up some things here. Order. Cool. Okay. So and just a reminder for the clock, it's 12 minutes because we're in the final. Okay, cool. I was just looking at the clock there and just figuring that out. So if you're ready, then you have 12 minutes to present your solution. Good luck, and you can start right now.
Thank you. Good morning, good evening, everyone. My name is Bernardo. Today I'm presenting the problem number 10, droplet sanding fingerprints, representing the team UFMG. So this is just a quick overview of this presentation. We're going to start, as always, by looking taking a look at the problem statement. We're going to look at our experimental setup, our apparatus and experimental data method. Then we're going to introduce our theoretical model, results, and finally the conclusions. So the problem statement wants us to study the formation process of this phenomenon when a droplet falls into a surface, and it also wants to know what parameters of the droplet can be inferred from the resulting crater. So this is just a quick video we made to represent the problem, and here is I just wanted to show this extremely beautiful place where we took the sand here in Serra da Lapinha, Minas Gerais. And this is just a quick problem overview view of the image. We were taking a look just to see how we could how we could control the size of the droplets. So here we have an extremely beautiful camera, a high-speed camera. We could observe the process, the dropper and light so we can see everything is going on here. So here we have just a quick video to explain the phenomenon. So our proposition is, the phenomenon is, we have a droplet which will collide with the surface. This is a hydrophobic surface. And our proposition is that when it collides, we can observe that it reaches a maximum deformation. And our proposition is that, our hypothesis is that this maximum deformation of the droplet is the crater, is the maximum radius of the crater when the crater formed in the sand, in the granular media. Here we can observe a view of this droplet colliding with the granular media, and this is actually what we observed in the experiment. So let's take a look at the theoretical model, because the problem statement wants us to explain how explain the processes. So here we have let's start by a simple example. Here we have a droplet at static position in a hydrophobic surface. This is approximately the shape of this droplet, and here we have some pressures occurring in this system. We have the Laplace pressure, the hydrostatic pressure. We also have this parameter, which is the capillary length, which represents what could be an approximation to the radius of this droplet. And the most important term, I want everyone to pay extreme attention to this term. This droplet is immersed in a gravitational field. And I want to draw your attention to this term because it will appear explicitly in some parameters. So we want to get some information from this system. So what we can do is apply the drop stability condition. What is this? We know that the droplet is stable. What is the condition of stability? We could observe this is a gain between pressures. We want that the Laplace pressure to be equals the hydrostatic pressure. And when we apply this condition of stability with these equations, we know the equation of the hydrostatic pressure, which is equals rho g h equals, and where rho is the density, g is the gravitational field, and h is the height, the height. And our height is actually 2 times the Laplace pressure, Laplace capillary length. And here we have the Laplace pressure, which is a function that depends on the tension of the surface over the capillary radius. When we apply this condition of stability, we get we get to know what is this parameter, the capillary length, and observe that these capillary length depend explicitly on the gravitational field. So, but this is not the problem we want to solve. We want to solve a problem of a droplet colliding with granular media. We are going to make some assumptions here. We are assuming that the droplet is approximately a ball, a sphere. And this sphere is colliding with the system and suffering a huge acceleration we are calling G star, which will be clear for a second, in a second. And after these dynamics occur, I said that the droplet will face some maximum deformation, where we have this parameter Rm, which is the maximum deformation, which will be the radius of the crater. We will leave printed in the crater. And here we have a small lambda star, which will be the radius of the capillary length. So we cannot, we would like to write down what is the capillary length and how we can make it. What we're going to use is the Einstein's equivalence principle. Because when we use the Einstein's equivalence principle, it states that we cannot distinguish an acceleration frame of reference to a external gravitational field, and we can say that it is equivalent to say that this from this droplet is submerged in this gravitational field with same modulus of G star, but opposite directions. So we using this principle, we are going to say that our capillary length star, which is this dimension, equals these terms, and this is the acceleration of the system. When we can't say that this is actually in gravitational field, because Einstein's equivalence principle. So let's consider some parameters. Now our task is determine what is G star. So to define what a G star is, we are going to assume conservation of energy. There's when we assume conservation of energy, we can use Torricelli equations, and we can determine what G star is. I want to make a point that this system is not conservative in energy, but we are interested in the order of grandeza of these of G star, and this is a good approximation. So another quantity that is conserved in the system is the volume. We know that the volume of the sphere right here in the initial state is equal to the volume of the deformed droplet. And when we are assuming that our initial droplet is shaped as a sphere, and the final is approximately a cylinder. So we can say that this law follows when we have the r cubed, which is the radius of the sphere, is proportional to this term of the final volume. And why this is important? When we get together these two informations, we result in a power law. And this power law is extremely important because it's saying that the radius of this crater follows a rule of a power rule of 1/4. And this parameter right here is what we call the Weber number, and Weber number is a number associated with the energy of the system. So here we have just a picture of how we are making the data analysis. We have a droplet here, we have a measurement device to calibrate, and how are we actually making the measurements? We are making the measurements using the tracker, and here in the tracker we can set 3 points, and in these 3 points we can ask the tracker to put a circle, and with this circle we can get the information of the radius and the diameter. So this is what we do. What we're doing, we're collecting these data, and we have the maximum collecting these data, and we all remember that we want to find this power law. And by collecting the data, we could use the diameter, and here we use the right diameter of the droplet. We got this graph. But how we did make linearization and a linear regression of these points right here. So this is the graph. We made the linearization of this graph and linear regression, and we observed that this slope, which is the parameter we wanted to find. So we wanted to find a fourth, and we found 0.7 plus or minus 0.002. So the conclusions, we observed the power rule of 1/4 with a linearization and then a linear regression of the data. And the problem wanted us to identify what parameters we could infer from the crater. And the only parameter we were able to find by these processes were the initial potential gravitational energy of the droplet from the radius of the crater. Thank you, everyone. I'm now open to technical questions.
Thank you for your presentation. Was an interesting development on this problem. Well, could you go back to the slide number 13, please?
Sure.
Or show your data. Yeah, that's it. You only measured the initial height and the diameter of the final fingerprint shape.
Yes, correctly.
Okay, there's any information about the intermediate state?
No, we didn't make any measurement of the intermediate states. We were interested in the initial condition and then the final state.
Okay, thank you. Can you go back to the next slide? Go on. Sorry.
Right.
Can you please open the slide with your theoretical development?
Sure.
Just pass through them slowly, please.
Okay, I'll go through the order. We're going here, then right here.
That's it. Thank you.
Okay, thank you.
All right. So now the opposing team has 3 minutes to prepare themselves.
Hello, Mateus. I will be the presenter, the opponent.
Okay, so please, Henrique, just give him the permission to present.
Great, thanks.
Cool. Meanwhile, I'd like to thank you all the people that are watching us through YouTube. There's lots of people here cheering for the teams, and from all teams as well. It's so cool. Yeah. There's even a bunch of emojis. It's pretty interesting. All right, you still have 1 minute. You have 20 seconds. Ten seconds. Lauro, are you there?
Yeah, we would like a timeout, please.
Okay, so 1 extra minute. Just reminding all the teams that you have 3 timeouts that you can take throughout a fight. Since this is the final fight, you know these timeouts have been resetted. So, I mean, all fights, you've always had the chance to do it. So,
Can you see my screen?
yes, we can see your screen. Yeah, but it's on the 3rd slide now. Okay, cool.
Okay.
Yeah, if you would like to start, then
Yeah. let's go.
Let me just check on the minutes. You have 5 minutes to present. Go ahead.
Well, thank you, UFMG team, for your presentation. It was a very nice development on this problem, and thanks for such a complete explanation on the theoretical model on this. When I was searching literature, I could not find something so detailed as you show it, but there are some topics to discuss on your presentation. The first point is the statement of the problem, which says, when droplets fall on a surface covered by a layer of sand, interesting patterns are formed. Study the formation process. What parameters of the droplets can be inferred from the resulting crater? So the objectives are two. First, study the formation process, and you show this through your theoretical development, and then show it a result about it. And the second one was what parameters of the droplets can be inferred from the crater, and sadly it was not answered or even mentioned appropriately. Well, as positive aspects, you did a very fine control of the droplet radius, which has to be appreciated. Also a good experimental apparatus, which could be also better used to obtain more experimental results to support your theoretical findings. Also, you found a power law which is consistent with literature. I just made a citation of that kind of result, which could also improve the force of your argument. Okay, and also showing that this is a known result in literature. Well, as a clarifications, we could point that we see that there was a lack of details on the experimental procedure, how exactly the fingerprint parameters were measured. You did not show it this data properly as we should expect. Also in slide 5, you showed some videos, and I'm not sure if they are yours, self-made experiments or not. You also, in your theoretical developments, showed a hydrophobic model of a droplet in a hydrophobic surface, which based the model, and then some effective constants were introduced, and we would like to hear some clarifications about introducing those effective constants, and if how they were determined for your experiment. And also in the theoretical model, you expand, I counted something about 8 minutes of a presentation just talking about your theoretical model, which is a lot. So it lacked a lot of experimental results, experimental development. We missed that in your presentation. It will be great to talk more about that, those procedures you use it. And finally, I could gather all those questions in these two main topics, which are, well, the variation of parameters, which is in the statement, and it was not properly approached. You only varied diameter and the initial height, and this was the only connection between a parameter of the fingerprint and a parameter of the droplet that you could make. But there are other parameters of the fingerprint, like the shapes, the various shapes they can admit and take depending on the initial height you give. There is a whole phase diagram to the type of grain and the initial height you give to the droplet, and that was not explored at all. And so we'd like to discuss how you would do that in order to improve your solution. And also, and that's it. We can begin our discussion on that.
Okay.
Hello,
Thank you. Sorry.
Yeah. First of all, I'd like to thank you again for your presentation. And besides those questions I established here, I would like to ask you to share your screen again for us to discuss your work and
Oh,
the
sure.
way you
But
presented.
actually, I wanted to see the questions again. I'm sorry. I think I got a print over
Yeah,
here.
I will tell them to you.
Okay.
In the preferred
So
time.
okay, I'm
Okay.
sharing my screen. Right. I'm sorry. Which one do I share? Okay. Can you see my screen properly and the slides are moving? Can you
Yeah.
confirm that?
Yeah. It's great.
Okay.
It's great.
Okay. Oh, thank you. So we're going to start right here. I remember it was a question. No, these videos are not mine video. Are our videos. I don't know what happened, but we had the links over here, right down over there.
Oh, okay. Yeah, that's just a
technical
a
issues.
technicality, but the
Yes,
credits for the authors should
yeah,
right?
actually, all those videos were taken from these references, which are right here. One of these. Yeah, that was the first question.
Okay.
Let's move on to a
That's
more
okay.
important question.
Well, about
okay.
your experimental procedure, in slide 13, could you open it, please?
Yeah, sure.
In slide 13. Yeah, you showed us the experiment you did. Did you perform more experiments, like maybe changing a parameter, like the grain size or something like that?
No, we use only that grain. Actually, we made this experiment several times. We tried to do the experiments first with grain we found in construction zone, and that grain is not thin enough. So we couldn't observe these. The data was not actually what we were expecting. And then we found that grain, which is a lot thinner, and the process is actually worked as we expected. So you asked about the many times we did the experiment. It was an exhausting experiment. I think we spent more than 27 hours doing this experiment. So each one of these points we can see in the graph right here were taken from the height. We tried to take the same height with our device, and we were measuring a lot of times. I think it was an exhausting process, and we had a lot of more than one person doing these crater analysis tracking, which I think it was one of your questions. What we determined as the crater? We're determining the crater as after the droplet leaves the print in the sand, it retracts.
Okay.
And our proposition is that the maximum deformation is what is the crater size. So we measured the crater right here. It is actually difficult to see in this image, but when we zoom in computer, it's actually really good. It really is the same.
And did you only observe this shape of fingerprint or others too?
Yeah, for higher order, when we get as we keep increasing the height of the droplet, the shape will start to behave in a different way. But there is actually
because there are other
reference.
kinds of shapes you could find. Like you see, in literature they find shapes like donuts, small spheres, also inner rings and outer rings. This kind of parameter
yes, but here in one of these, I don't recall from the head, but here in the literature we observed that
characteristic of fingerprint.
They observed the same characteristic the fingerprints we observed, and they varied the height from a couple millimeters to up to 12 meters, which is a range a lot greater than we could measure.
Great. my last question will be,
Right.
how would you train your apparatus to measure more parameters relevant to it?
More parameters relevant to the system. So how we do it? It is actually an extremely difficult question, because what we measured, what we found in our experiment was what is the height, what is the potential energy of the system based on the crater. But if we know the crater and we know previously what is the actually, suppose we know the density of the material we're working with, we could determine what is the mass of the system and of the, actually what it's called, the droplets. So with what we have right now, we would need some previous background from something about the drop.
Okay.
Okay.
Thank you.
All right, now all teams can join the discussion. Yeah.
Yeah.
Is it all team discussion or the reviewer technical questions?
Oh yeah, no, sorry. Yeah, I'm sorry. Yes, it is the.
I was waiting for that.
The technical, yeah, the reviewer's question for the opponent team and the presenting team.
So for the presenting team, how did you measure the velocity used on the Weber number determination?
So as you observed, there's a velocity in the Weber number right here. We didn't actually measure the velocity. What we observed was that this radius it scales with a power of 1/4. We didn't measure this thing, but we could measure with our camera if we wanted.
Yeah, but you plotted the radius as a function of the Weber number, correct?
No,
or
we
the
plotted
height. The height.
We plotted the diameter of the system as a function of the height.
Yeah, so the Weber number, did it have a constant velocity that you consider in the equation to have the 1/4 power law? Because there's a V0 there, correct?
Yes, this is let me go back here in the image. The V0 is the velocity in which the sphere collides with the medium.
Correct, and that changes with the height you have, right?
Yes, it changes.
So what value of the velocity did you use for the fit?
We didn't use any parameter of velocity. When we fit, we're not actually just fitting this graph. We are taking doing linearization of these this formula, applying natural log in both sides. And we make this linearization, we can make a linear fit, and the linear fit will be this parameter right here, the power rule.
Okay.
All right, thank you very much. Then now the reviewer team has 1 minute to prepare the presentation. Now 20 seconds.
I want a technical timeout, please.
Okay, so 1 minute will be added at the end of this period. 45 seconds. Fifteen seconds.
Can you see my screen?
Yes, yes, we can see it.
All right. So we can start.
Okay, you have 3 minutes to present, starting now.
Hello, everyone. My name is Rodrigo. I'm going to be the reviewer for the fight in the droplet sending fingerprints problem. First of all, thank you for the reporting team, Bernardo, and for Lauro in the opposing team. So first of all, a few aspects on the reporting team. Congratulations on your beautiful presentation. It was very visually appealing, and the theory you showed us was really interesting to calculate the maximum blast diameter of a droplet. And a very nice touch to include the Einstein equivalence principle. Congratulations. And you did give us a relationship between the droplets parameter and the diameter as it is asked in the problem statement. However, I feel like the problem statement clearly dictates that the problem is for a layer of sand, and the experiments did not provide details of how the sand was used. Was it a thick layer? Was it a very thin layer? And the theory did not discuss the sand at all. So that's an interesting point. I feel like that should be included. Is the droplet the same falling on a granular surface as it is falling on a hard surface, right? Also, the lack of references on the page 5, on slide number 5, and did not discuss the resulting format of the crater as well as the full formation process. And I feel that's very disappointing since you have a very powerful slow motion camera, right? I think you would have valuable insights on this. So on the opposition, I would like to congratulate you on pointing out the lack on the full formation process details, as well as the fingerprints. Pointed there's a bit on the experimental details that is lacking. There's no reference on slide number 5. I think there was some nice details on the theory that you pointed out. And also, you presented a discussion to improve the experiments, which is a very nice thing that I guess the UFMG team can do. But you did not point out that the theory does not depend on the layer of sand, and I think that's a big problem on the theory. And you did not discuss at all the layer of sand part of the problem statement. And you said that the theory does not describe as a relation between the droplet parameters, but it does. It gives a relation of the Weber number and the details and the maximum diameter, and did not ask how the velocity was determined for the Weber number fit. That's also a part that I think was a bit nebulous. So first of all, congratulations again. I would like to open up for discussions, and maybe I'll stop sharing and just talk to you guys about the points I want to discuss. Can the theory be adapted to consider the influence of the granular surface in the bottom? You could maybe show us. Maybe show us again. Yeah.
Okay. I'll share my screen again. But here, just let me know when you're able to see the screen.
We can see.
So let's see the theory again. Actually, you're right. Where is it? Our discussion is mainly based in surface, rigid surface, surface, and we actually don't. We were doing some approximations because we know, like here, we are only looking at the order of magnitude of this G star, and we are making some assumptions of the system, because it's not actually what will happen in with a granular material, but we actually didn't know how to add the dynamics of like molecular dynamics. So I don't know, to describe the motion when these hit the radar part.
Yeah. Do you agree, Lauro? Do you think there's a a way to improve in this theory to consider the dynamics of a granular surface?
Well, when I analyzed the literature on this, I saw that the main models also considered first a model on a hydrophobic surface, as I noted in my presentation, that they also that UFMG team also developed on this hydrophobic surface, and that this also collapsed various different experiments on different grains sizes on the same line, and that turned this theory very reliable. This was not shown by the FMG team, but it's a very interesting data to present and support their results. So I think this theory can be appropriated, yes, but maybe there may be some deviations on this power law, depending on other parameters of the system, as pointed also by other references in literature, which showed some deviations of it.
Yeah, I agree. Yeah.
There are more than one models to this problem. So that's a point to consider.
Yeah, and I want to go back to the discussion on methods to improve the experiments to corroborate or to disprove the theory. I believe that an interesting topic would be how to see how the theory holds up in different types of sand, right? So what do you believe it would be most impactful parameters to change here for both teams? Yeah.
We observed that. Okay, we can start. Sorry.
Go on. Your theory.
Okay. No, thank you. We observed that, if I understood you right, we observed that the sand does affect the problem, and we observed, but on our experiments, we actually don't have the data presented here in the presentation. But when we are trying to do the experiments with a thicker granular media, it didn't actually work properly. So the thinner our proposition, what we are assuming is that the thinner the granular media is, the better the theory holds.
So this is, you kind of found a limit in which the theory is appropriate or not, based on the point Rodrigo pointed out, right? Which is the influence of grain sizes on this problem, and the fact that the hydrophobic approximation is not that valid when you have a granular media which is not thicker enough.
Yeah, it's interesting because we see on the fingerprint that part of the sand is absorbed into the droplet, right?
Yeah.
So it clearly isn't actually hydrophobic. It is absorbed, right? And that would also change the volume in the end. Yeah.
Yeah, and the shape of the fingerprint too, which you, Bernardo, could you observe other types of shape besides those you found, just because of this parameter, the granular size?
Yeah, Bruno from USP, could you please chip in? I saw your hand raised.
Yes, I would like to ask about the parameters inferred from the crater, because the reviewer pointed out correctly that indeed the theory predicts the Weber number, but the reporter didn't mention this in the presentation. I mean, the theory can also predict other parameters, but the reporter, I believe, but the reporter didn't mention this in the end. It just mentioned the potential energy. So I would like to ask if why he didn't mention the Weber number, and also if there are other parameters other than potential energy and the Weber number.
Okay. Yes. Okay. we mentioned the Weber number that is right here in this equation. It is a parameter related to the energy of the system. And we didn't measure, we weren't interested in the V0, this V naught, because V naught is the velocity of the sphere when it hits the ground. We would like to understand what we usually when we are solving a problem, we have an initial conditions and then we want to know what is the result. Here we have the opposite direction of the problem. We have the result right here, and we're trying to know what was the initial conditions of the system that made it this problem. So this velocity is not actually what we were interested.
I have a suggestion for you to do in this case. Well, this is the impact velocity, right?
Yes.
Well, the sphere, the droplet did not touch the sand yet. So you could just use conservation of energy to estimate V naught, input in your equation, and then obtain a full result and full analysis of your problem.
Maybe we could move to another point here. Hannah from UFMG, if you could.
Actually, I just want to add something to what he said before I get to my point. It's because we use conservation of energy. Gabriel was going to talk about it, and he has the hand raised, but he didn't talk yet. But what I was going to say is because it was pointed out that it cannot, the approximation of the surface being hydrophobic, it's not possible. But I think it is possible, because in the moment that the water hits the sand, it can be approximated by of being hydrophobic, because it doesn't really infiltrate in the sand, you know.
Yeah, that happens when the grain size is small enough, as we were discussing, right? But it is greater. Bernardo and I think you also observed that there is penetration, right? And the situation changes.
Okay, yeah.
Then
so
I agree. My point was more.
We have the last concluding remarks by the presenting team. You have 1 minute. Well, you have. Well, did you hear me? You have 1 minute to make concluding remarks.
Sorry, I got it a bit confusing. So I want to thank everyone for all your comments. I think that this was the best discussion I had in all these tournaments already. I loved it, and we discussed some things, important things that we can adjust in our theoretical model, such as we could apply like some conservation of energy of the particles flying around, and this is the I agree with I want to say that it was a good presentation and discussion. Thank you, everyone.
All right, so now we move on to the next stage. Then it's questions of the jury. You have 5 minutes, so please keep it to one question each, please. Or if we don't fulfill the entire time, then we can move on to more questions. But please, jury members, raise their hands. Okay, Barbara has a question. Go ahead.
I think it was the last one to raise my hand.
Really?
Yeah, Claudia was the first, and Mattel's and me. Yeah.
Oh yeah, so Claudia was the first, and it didn't show here on my screen. So Claudia, please, you can ask away.
Okay, some people identified the size of droplets, but I didn't see it. I didn't identify in the presentation the size of the droplets, and also whether you could vary the size of the droplets. Could you clarify?
Yes, actually, we didn't actually made it clear explicitly what was the size of the droplet, but our dropper, or our device we were using to drop, it actually made extremely equals sizes of droplets. The droplet wouldn't fall if the size of the droplet weren't the same. We made these calculations, and we should have went here.
But you have a number? Do you know the diameter of the droplet? from the camera, or?
No. Right now, I don't know this.
Okay.
Just to complete his answer,
Sorry.
can I? The size of the droplet is it's implicit on the density of the fluid that we are using on our formula. So it's actually implicit there. So we more or less take it into account. So thank you.
All right, so I think the next jury member is Mateus to ask. You can ask away.
Yeah. So this question is for the three teams. So let's say you are inside an elevator doing this experiment. The elevator is accelerating downwards. Will the radius of the droplet, like the radius of the fingerprint, increase, decrease, or stay the same?
I can try that.
I think it will decrease
on the grain size.
I'm sorry.
Sorry, reporter team.
I'm sorry, I didn't hear the Laura was speaking. Laura, can go on.
And from the opposing team, I just said that it depend. My guess, it would depend on the grain size, as we were discussing. The grain size influences on how the cohesion, how the penetration on sand is relevant to this problem. So if it is a lot and there is this acceleration downwards in this problem, maybe we could observe different shapes depending on this penetration of sand, changing this parameter in this way.
Okay, next team.
I think that if the apparent gravity increases from the acceleration of the elevator, the crater would increase because there's more energy to the droplet with a higher velocity. So, yeah.
And the reporter.
Yeah, I think the diameter of the crater will decrease.
Okay.
If the elevator is accelerating downwards.
Okay, thank you. So let's move on to the next
Mateus,
jury member.
just sorry. Was the elevator accelerating or at constant velocity, Mateus?
Accelerating downwards.
Okay, thanks.
Okay, so please, Barbara, you can ask now.
Okay, so the question of the problem was literally what parameters can you infer from the creator? If the three teams could be very quick and concise, which parameters can you infer from the creator in your opinion, and how?
I'm sorry.
Which parameters of the droplet?
So the only parameter we identified was the initial energy, potential energy.
Right, but imagine there are unlimited resources. You don't have any limitations for your experiment.
Okay. So actually, I suppose we would be able to identify like the radius of the size of the droplet.
Well,
I believe that from the
yeah. Go there.
Go ahead, Laura. Sorry for that.
Okay. In my research in literature, I found many of these examples. There's a phase diagram of height, initial height, and the grain size. So for sure, and this also relating the shape you observe. So if you know the shape and also know the kind of beach you are, for example, or the initial height you are, for example, you can deduce the initial height. So this is a parameter you can vary. For example.
Yeah, I agree. If you have the information regarding the Weber number and the droplet, you will have the height, but you would need to have one of those.
All right. I think we can move on then to the next jury member who's going to ask is Alexandre. Please ask away to any of the teams.
So, along these lines of infinite resources, so none of you mentioned the depth of the crater. I know it's very, very difficult from the apparatus that we have, but I mean, can you give an insight on how important that would be to the overall problem, and how would you go about to measure it? For the three of them.
We also tried to measure the depth of the crater. We failed horribly trying to do these measurements, and I don't know how we would be able to do it. I don't know, by some sonar, some sound, using a sound. Sound sensor. I don't know how to do it without disturbing the system.
Well, as I see, there is a way of measure the depth of the crater, and I found papers doing that. They use lasers, and then they measure reflection and diffraction, and through that they can do a complete map and a level map on this problem, and that they can measure depth. And what they observed was that as the impact velocity increases, also increases the depth you observe in most of the shapes. So that's this dependence.
Yeah, there's another interesting result is that the depth linearly increases with the diameter of the crater, and it's a constant fraction for all energies. There's a paper very interesting about that, and there's an energy scale where there's a rebound of the water where you can visually see the bottom of the crater, but you would have to get the right energy dependence. Yeah.
Okay, thank you very much. So now I believe the juries will decide their marks. So please, you have approximately 1 or 2 minutes to do so. Yes, please grade the teams. Okay, I think we're almost done with the grades. All right, we do have all grades now. So we're not going to review any of those grades because this is the final. So we're just going to give like a 5-minute break into the next round. Okay. And we'll even clock it this time, and just share a screen here with the thing. Oh, let me just also remind what's the order. Okay. We have it here. We just I think I'll put in that in this this image. This image is nicer. Wait, oh, I'm almost announcing the break. Let me just make everything ready. Okay. I can share the screen. Okay, and then we're gonna be back in 5 minutes then. And that's it. Thank you all for watching on YouTube. We'll be back soon.
Pode me colocar já como moderador, por favor? Alô?
Colocar quem? Desculpa.
Eu vou estar apresentando, você pode me colocar como moderador?
Ah, tá. Vai lá, Henrique. Põe então o Lucas.
Pronto?
Acho que deve ter ido, né? Não sei. É o Henrique que controla aí. Ele vai fazer isso.
É o Lucas Unicamp.
Okay, I think oh wait, let me just organize some other stuff here, but I'm waiting for all team members to come back.
Você consegue ver minha tela?
Sim.
Perfeito. Let me just... I don't know how to turn on my camera from this. Sorry. Start video. Okay. Can you see me?
Yeah.
Yeah. Nice.
Yeah.
So
wait, we're not starting yet. I think I'm just waiting for
just to check if everything is right. Is all right.
Okay, yeah, but I'm
yesterday I had some technical problems.
Still waiting for the other teams to show up. So all jury members, at least, if you could just show up or write something in the chat so that we know you're there. Then we can move on in the second round. Oh, yes. There will be space for jury comments. I think just for sake of time, this last round we didn't do it, but we should have. So sorry for that. We were just trying to keep good track of time. But I believe all jury members are here. Right, let's see. So we have 5 jury members. So Barbara is here. We also have Mateus Farias and Edward and Claudia Lenz. And is someone else missing? Alexandre, let's see. Oh, he's also there. Okay. Yeah, good. So our teams are ready too, I suppose. If you're ready, then just from UFABC, someone could say if you're ready, and from Unicamp. Oh, Unicamp, yes, I see.
We are ready.
And USP too, are you ready? Just USP maybe is not gonna. I don't know if they're observer this.
We're ready.
Okay, UFMG. Okay, cool. Yeah, no, sure. All right then. So without further ado, then. We have 12 minutes to start. Wait, let me just. I received a message here. Okay, 12 minutes to present. Starting now.
So, hello everyone. I am Lucas Roberto, and I'll be presenting problem 5, sparkler. First, let's remind the problem statement that says investigate the burning process of a sparkler. How far can the sparks fly, and what determines the size of the flame? So, first, let's define what I mean as a sparkler for the course of our presentation. We will define as a sparkler as a slow-burning metal handheld fireworks that emits incandescent sparks. And our main object of study will be the commercial sparklers that has this composition: barium nitrate as oxidizer, aluminum and steel fillings as metal fuel, and dextrin as a binder. I would like to stress that we did vary some of these parameters, such as the material of the binder and the mass of the sparkler, but for question of time, I will be only focusing on the standard commercial sparklers. We can discuss more on the fight. So first, here we have our first phenomenal observation, where we can clearly see some aspects of the system, such as the emission of thermal radiation in form of visible light. We have a heat generation on the sparks, on the sparkler. We have sparks ejection, and these sparks in the air, we can see they clearly branch, and when they branch, eventually they will fade out. We will say that we are only interested on sparks that are currently glowing. So when they fade out, they are out of our system, and we are not more interested in it. Here we have some assumptions of the system, such as we will assume a black body model, a uniform internal temperature of the sparkler, isotropic branching explosions, and overall quick chemical reactions. So we'll separate the sparkler in two main stages: the burning process, where we have the emission of the sparks by the sparkler, and we want to study how this light comes into existence. And the second part, the sparks flight, where we want to study the cooling down behavior of the sparks, and why and how they branch. Also, one thing that is on the problem statement is the flame size, and I would like to define the flame size as the volume of a sphere that is defined, that has a radius defined as the average distance of a spark in a certain point of time. And this spark needs to have a temperature above its incandescent temperature. So here we have the main reactions of here we will discuss the burning process that starts when I hit the sparkler with an external source of heat, such as a lighter. And when this happens, the bearing rate will melt, and the components will achieve an activation energy. When this happens, we have some chemical reactions, such as the combustion of the binder and the redox equations that will transform the nitrate into oxide. This reaction will produce a heat of formation that through that we can see that this is an isothermal reaction. Then the gases produced by the sparkler will heat, and with this temperature, they will expand nearly adiabatically, and this pressure will eject the sparklers. The condition for continuous burning of a sparkler is that the region below the current burning region receives an energy above its activation energy. So now we know that the temperature is one of the main factors of the sparkler. And to study the temperature, we decided to construct a homemade spectroscope, and we did this using a sheet of paper, lamina blades for the opening, and a DVD as a diffracting gauge. To calibrate our spectroscope, we used the spectrum of the light spectrum of a fluorescent lamp and of a burning sodium. These spectrums, here is the plot of the intensity of the spectrums through the pixels of our image, and we can clearly see the emission lines. These emission lines, these peaks, are well known on the literature, and we can map them with the pixel of the camera. Then we can fit this and have our equation that relates the wavelength with the pixel. So we did the same with the spectrum of the sparkler, and also we calibrated, the previous calibration was on x-axis, and we calibrated on the y-axis using a transfer function with a non-black body that was the light of a car. Then we fitted this curve using Planck's law, and with that, we could measure an experimental temperature for the sparkler. And we did this for the whole burning process of the sparkler. So we did a bunch of fittings of a sparkler spectrum, and we could see that the temperature of that the sparkler burns is somewhat constant, and this is around 1,381 Kelvin. So when the sparks are ejected, they will fly through the air, and due to the high temperatures and the barrier nitrate being molten, the sparks will have a behavior of molten oxide. So they are droplets in the air, and we can see this through some videos of the literature, where you can see that these sparks are actually spheres that wobbles in the air. So the sparks are droplets. As we know, the sparks are droplets made of parts of the sparkler. So the reaction that happens in the sparklers will still be happening on the sparks. So inside these droplets will be the formation of gas bubbles and of the gases of the sparkler, and these gas bubbles will heat and then expand. With this expansion, they will promote an internal pressure, inside the droplet, and this pressure will promote an internal force that when this force becomes greater than the surface tensile forces of the droplets, the spark will branch. We also study experimentally the numbers of branches that happens within sparks. We did this for a sample of 100 sparks, and you could see that the maximum number of branches is 2, and the most common is 1. Then we started studying the temperature of the sparks in relation to time. We wrote down the equation of cooling, because the spark is in contact with the air, losing energy, and then we could predict the time, the temperature in respect to time, and in respect to the radius of these sparks. When the temperature of a sparkle drops below the Draper point, that it's a temperature where all solid and liquid matter glows, they will fade out. So when this happens, we'll say that sparklers are out of our system, and that the time to reach this point, we will call it as a time life of a sparkler. We can then isolate this time and wrote down on this equation, and we can predict the time life of a sparkler in respect of their radius. We can see that when the sparks branch, the radius will decrease, and then the time of life of the sparks will decrease. And we can see this on the videos. When they branch, they right after this, they fade out, and we can no longer see them anymore. We also, with this, we predicted the time, and we also measured the time within our videos when we could compare them to see that we have a coherent results of our theory. We also made a histogram of the numbers of sparks, from generated by this branching, and you can see a nearly Gaussian distribution of this. And we have an average nine sparks resulting from these branchings. Then we can observe a spark in the air, and we can write down the diagram of forces. We'll have a drag force and then a gravitational force pulling down. And with these forces, we can write down Newton's second law and have an equation of motion that will describe the sparks in movement in space with respect to time. And this equation, we can see some parameters of the spark, such as the radius on this gamma factor. This was our experimental setup. We maintained a constant our camera settings, and we also recorded the sparkle burning from 2 points of view, a side view and an up view, to have information of all angles. And we used the software tracker to get all this information. So with the tracker, we could mark points of the spark in the space, where you can see on this graph, we have the position of the sparkler within the camera plane, and we can see their branches. But more importantly, we could track down the experimental points for this velocity, and with our equation of motion, we could fit them, and with this, get the initial velocity that sparks are being ejected from the sparkler. We did this for a bunch of sparklers, and you could see that this velocity, this initial velocity, is somewhat constant. So they are ejecting that. In average, our sparklers are being ejected with somewhat the same velocity, and this is really important. Then we can attack the main questions of the problem. First, the maximum distance, and I would like to stress out the maximum distance problem. It's a problem that has a very low probability of happening when I am burning a sparkle on maintaining on constant pressure and temperature. First, we need to assume that the branch, the children of the spark, always we are only interested in the branch of spark that happens within a plane, and this plane will be defined using cylindrical coordinates. So we have an R that says the distance, the radial distance of the spark to the sparkler, and we also have the Z plane that dictates the vertical motion. So this branching will always happen radially further from the sparkler. Then we need to assume a maximal angle of launching to get the maximum distance, and also we need to assume a maximum lifetime of the sparks, since we want to have an optimal maximal distance. So the maximum distance problem, it will happen in a 2D plane, and then knowing this, we can write down the motion equations with respect of each axis, and we can see that depend on the initial velocity that we got it from our fittings. And then we still need to know the optimal angle because of the drag that will be a bit lower than 45 degrees, and the optimal time that sparks branch. To do this, we used a brute force recursion of the problem, and we could obtain our maximum distance that is around 19 centimeters, and we can see on this graph where each sparks branch. So having our maximum distance and using tracker, we could mark the points and measure a bunch of points of distance that the sparks fly. And with this, we could obtain an average distance. And using our definition of size of the flame and our average distance, we could obtain the volume of the sphere that is our size of the flame. So in conclusion, we define our object of study, the combustion sparklers, we investigate the burning process, we developed a spectroscopy study using a homemade spectroscope and obtained the sparkler temperature via black body model. We explored the sparks droplet nature and why and how many branches will happen. We constructed a cooling model, we investigate the sparks motion experimentally and theoretically, and also we developed a model that predicts how far the sparks can fly and the size of the flame. So within this, we can say that problem statement was solved. These are my reference. Thank you for your attention.
2 minutes for technical questions.
Yes, I have some questions about the some slides. If he could come back a little fast.
Do you know the slides?
Yes, this one I'm talking about the sparks branching twice. Just wanna
branching
something.
Which one? The where you have the histogram here?
No, before that.
Before that. Here.
Yes. What do you call branching here? Like,
so
is the number of sparks that are branching, or is like how many times it branches?
Let's say we are using tracker and have a sparkle flying. This spark will branch, and then we have a bunch of new tiny sparkles. These new tiny sparkles can also branch. So we have one branching, and then when this tiny or the sparkle branch again, we count this as the number of branches. And the maximum that we observed was 2.
Okay, another slide is the one where you talk about the bubble of air that it is inside the spark.
Yes.
And how did you come to that conclusion? I'm sorry, I was a little lost in this moment.
Sorry, I was a bit fast. The sparks are made of the same materials of the sparkler, and we know they are molding material, right? And on the reaction of the sparkler, we see that have the generation of CO2 and nitrogen gas. So inside these sparklers, we can also say that this reaction will happen, and to observe this event experimentally, we can see on this GIF video from the literature where we have these sparks where we can see the bubble expanding and then the branch of the sparkles. So it was due to these regions.
Okay.
I hope I was clear enough now.
All right. 3 minutes for the opponent to prepare the presentation. Meanwhile, we're getting really cool comments on the YouTube broadcast. Lots of people from the 3 teams. From the 4 teams, actually. They're here. Also, who's going to be the opponent? It's going to be so that we can set it up here.
Hey, the opponent is Renan.
Hannah, okay.
Do you guys want me to stop sharing the screen for the opponent share?
Yeah, that'd be nice. So please, he could just allow Hannah to share his screen.
Yes, sure. Hold on. Can I have a timeout?
Yeah, sure. So 1 minute will be added at the end of the 35 seconds you still have remaining.
Okay.
I hope one day during these breaks, we're going to say the Brazilian Physicists Tournament is supported by, you know? All right, so you have like 35 seconds. $21 seconds. Now 10 seconds. Five seconds. You're not sharing, okay? Well, the time is up, so.
Okay, I'm going to share my screen.
Okay.
And can you guys see?
Yeah. Go ahead. You have 5 minutes.
Okay, thank you. So first of all, it was a very good presentation. We really liked it. Here's the problem statement, but I think we're familiarized with it, right? So positive aspects. We really like the GIFs and the overall design of the slide. It's very, very beautiful. And we really like the theory too, and how well it was explored. And also the experiments were very well designed, of course. One thing that we would criticize is that the presentation was too fast and sometimes were hard to, pay attention and really understand what I was trying to say. And some things we thought that could have more focus, like you could have slowed down and give more attention to some things, but still good presentation. And we also thought that there was a lack of images showing how actually the data was collected. There were some for the black body radiation thing, but except from that, not much. Anyway, here's some things that we would like to discuss really. And the first one is about the temperature, how good it is to define how far it goes, and couldn't we use the initial speed of the sparks to also determine how far it goes? And we also want to know how many times were the experiment made, because you said you did a bunch of times, right? So how many sparkles you used, if there was any difference in burning them, for example. In our experiment, we burned sparkles made from the same factory, but we found different results. And the relationship between the radius and between the radius of the spark and the maximum distance it goes. You talked about it, but you'd like to for you to like re-explain it slower. And how did you measure the uncertainty is actually directly related to how many times the experiment was made. And the last one is that in our literature, we found that the sparks explosion were due to other mechanisms. It was because of the concentration of carbon that there is in the spark. And this is a phenomenon that happens not only in the sparkle thing we are studying, but also in many areas of metallurgy, right? So, and this is something that people who work in this field use to know about the concentration of carbon. So I want for you to discuss what do you think about this difference? Why do you think there was this difference? And if you found anything in the literature that explicitly told you that was the mechanism of the spark. So of the spark exploding, sorry. So I think that's basically it. I can stop sharing if you want.
Can we start the fight?
Yeah, sure. Go ahead. Yeah, it's 5 minutes.
Okay. First things first. Let me share my screen, please.
There you go.
Sorry. Share. Okay. First, you said I have lack of images on how the data was collected. Actually, I disagree. I showed my experimental setup. I think we want to see these images on the tracker software, but I don't think this has many changes on it. But continuing to other things that you pointed out, I will try to explain better now and more slowly. In respect to you said the temperature is really a good measurement, isn't the speed? Actually, the speed is really important. That's why I made the fit to obtain the initial speed. And this was one thing that we raised it. I think this is answered. We don't need to, do you agree, right? I have a graph of speed. And okay, moving on, how many times I did the experiment? Actually, we only need to burn some sparks, because burning one spark, we can have a lot of data in respect of a lot of sparks that are flying from the sparkler. And with these sparks, we could measure many times the velocity, and with these, we could decrease our uncertainties because we propagated it. And I think this was another question that you made. We propagate our uncertainties, and we had the uncertainty of the tracker that was the software that we used. Also, the radius within the distance, we did a graph of the radius in respect of the spark's lifetime, and the spark's lifetime is one factor of the distance that also depends on the velocity. And we wrote down the equation of motion for answer this important question. And so we have a relation of the spark lifetime within the radius. Do you agree that this is a good measurement for the use of radius, please?
Yeah, I agree. And let me just ask you something about the amount of times that you burned the sparkles. Use the same brand of sparkles, or did you try it with a lot of different sparkles, depending on the composition and all this kind of thing?
We actually we use it, as I said on the beginning of the presentation, we varied some parameters of the sparkler, but we used the same branch of the sparkler that was the sparkler Jupiter Estrelinha. And this is an appendix slides where to show that we also studied the variation of mass. But we also varied the bind of the sparkler. Instead of using dextrin, we used a phenolphthalein resin, and we could see a change on the time of life of the sparkler and the velocity of the sparkler. Also,
so in the time of life of the sparkle, that you mean the candle sparkle, not the spark?
No, the spark in itself, the spark that are flying. This is the time of life that we define.
Okay.
Yes. This is the spark flying. Also, I think the last point that you raised was about the carbon. And this is an important point. And this is a really interesting point, because when we have some kind of metallurgy event, we see sparks flying. Like if I hit a plate of metal with a hammer, we can see sparks flying. Or when I ignite a lighter, we can see sparks flying. And this happens because of the concentration of carbon inside the steel. So I think that you were a bit confused on the literature that you were researching, because this type of sparks, and also the sparks that we see on fire camps, they are due to the carbon.
But it was not confusing. It was actually very clear about this.
Let me finish this, please.
Sure.
We also have carbon on the sparkler. Actually, we have all the chemical composition of the sparkler, so we have the reaction. So we know what are being generated, and we have CO2 being generated, and this is due to the carbon inside the deck string. That's because our bubbles also have carbon and nitrogen. So there are two gases, but I think this is explained better.
Okay, but hold on. The thing that you read in the literature was very clear. They said that the sparks were the same phenomenon as the metallurgic one. So first
they are
thing,
not. Okay, sorry.
you said
Please
that
allow, the opponents.
Sorry, what?
No, please allow the opponent to finish his question.
Okay, you just hold on. I want to know, like, how do you know the composition of the sparks?
Okay.
How do you know it? How did you measure it?
May I respond, Judy?
Well, unfortunately, we ran out of time, but there's room for more discussion later. So now it's time for the reviewer to ask both the opponent and the presenting team for 2 minutes.
Just one question. Can we ask a timeout right now?
Who? Wait.
Unicamp team.
Yes, I believe so. Yeah, you can ask a timeout. So then we'll wait for this.
Just a technical question. It's not the review team now?
Oh yes, but the reviewer can ask the questions after the timeout. So maybe they have any issues there. I don't know why they asked it. But,
okay. I think I heard you saying that it would be the discussion between the opponent and the reporter.
Yeah, no. In 30 seconds, this will start. Like the questions from the reviewer to both teams. 15 seconds now.
Okay,
so.
thanks. Thank you.
All right, so now the reviewer
Mas tá falando muito, deixa o cara perguntar as coisas para você.
I do agree. Yes. But now the reviewer can ask questions to both the opponent and the team. Yeah, reviewer, you can ask.
Okay, can you go to the slide where you have the maximum distance of the spark?
Yes. Here, this one.
Okay. What is gamma? It's the same gamma from the first equation of motion of the spark?
Yes. This one, right?
Okay, yes. And okay, could you go back to the maximum distance?
Just to clarify, the R on the motion equation is not the same R on this graph.
Okay. All right. And could you go to the temperature profile slide?
Yes.
Where you have the cooling equation. No, sorry, I mean the cooling equation after the burn. What's this dashed line in blue?
Okay, this dashed line is the Draper point. It's where the temperature where the sparkler cool down.
And was it, I mean, did you measure this or is it from the literature?
It's from the literature.
Literature, okay. And where is do you have a proper reference for this?
Yes, there are on our references.
Because it's not in the slide.
It's on our references.
Okay. Thank you.
All right. So now the reviewer has 1 minute to prepare their presentation. Now it's 10 seconds.
Can you allow me to share my screen?
Oh, yes, yes. So
We will like a timeout, please.
well, thank you. Thank you for that. Please stop sharing, Team Unicamp. We're gonna, who's gonna be the reviewer? Just for me to be sure.
It's me, Bruno.
It's Bruno. Bruno Siqueira from USP, then. So please, Henrique, give him the authorization to share. Yeah, reminding the teams to have 3 minutes. Okay, so 3 timeouts that they can ask during the fight. Bruno, you're already allowed to share. Yeah, if you want to try to share. Share.
We want another timeout, please.
Okay, cool. One more timeout. Yeah, that's cool. So I think USP has one more. I think now USP has used their 3 timeouts, right? If I'm not wrong. Yeah.
Sorry, let me stop share.
Okay, no, you still have 15 seconds.
Can you see presentation?
Yes. I believe you're in the second slide there. So, okay, so the reviewer team now has 3 minutes to present. You can start.
Okay, good afternoon, everybody. My name is Bruno, and I'll be reviewing problem number 5, Sparkler. And the statement of the problem is investigate the burning process of a sparkler and how far can the sparks fly, and what determines the size of the flame. So there are the 3 main tasks, and the reporter successfully did the first one, and the second also, but it was not that clear from the model that they used if the answer was properly answered. So I mean, I think we should further discuss these mainly these other 2 tasks. Okay, from the reporter, the positive aspects is that they varied the composition and also, I mean, trying different sparks. sparklers. They have clear assumptions right in the beginning of the presentation, so and this is very important. There's a clear explanation of the spark mechanism, and they have a calibration of self-made experimental apparatus, and they determine the temperature of the burning from black-body radiation model, and they also compared the time measured with time predicted. And some ways to improve, they didn't mention clearly how the enthalpy is related with the reaction mechanism that they presented. They have they didn't explore much the literature about the spark branching. They just explained qualitatively the spark branching, but there are other mechanisms, and this we can discuss this later. The cooling model is just associated with Newton's cooling law, I assume, but it's also related with the reaction itself that is taking place in the sparkler. And I mean, I think slide 27 was very fast, and we can just explain it again. The temperature change in the sparks was not well explored with the other mechanisms such as oxidation and convection, and the distance calculated from their effective volume, we didn't understand if it was actually the flame or the most probable flame or the furthermost spark. So this needs some clarification. And he did not cite the 3D influence on the maximum distance. For the opponent, he correctly noticed that the presentation was too fast and in some parts with low focus and other mechanisms of branches, but he didn't notice the connection of dejection theory with the reaction occurring before the sparks is formed. And they didn't mention how they got the activation energy, and also they didn't notice that they only have a necessary condition for the reaction to occur, which is important, but I think it's, I mean, we can discuss if this is really enough.
Time's up. So now the three teams, the three presenters can discuss between them.
Okay, the first point I want to discuss with you is that about the branching mechanism. If it's only, I think the reporter said that the composition of the sparks is the same of the sparkler, and this is not quite obvious, and I would like to see if the opponent agrees with this claim.
I agree, especially because we found that the composition of the sparks is not the same of the sparkle. It's a completely different thing. And we think that it's unlikely that it's going to have the creation of gas inside the spark mid-air, and it's going to explode the thing. And this happens all the time, you know. It really looks unlikely for us.
Can I ask for to the opponents and to the reviewer to state what is this other mechanism that could happen, and how the composition of the sparks can be different from the sparkler? What other elements would be generated? Other elements are being generated in it, from what you said.
I would like the opponent answer first because I think it's more.
Yeah, sure. In our research, we found that the sparks, they are made of mainly the metal metal component of iron, and the iron has a certain amount of carbon, and this is what burns and later explodes the spark. Sorry, just like it happens in the metallurgic process, as we stated earlier. So what really is behind the branching thing, we found out that it was the metallurgical process. It's not because the spark is made of the same components of the sparkle, you know.
So, could you elaborate more on what is this process, this metallurgical process? What are the forces that are exploding the sparkle, please?
The carbon is reacting with the air and it's releasing gas, but now from carbon, and it's exploding.
So this is the mechanism that I described.
Now-
The carbon is reacting with the oxygen. They are forming carbon dioxide, and then this gas is expanding as well as with the nitrogen. That is
But
the
it's
other gas.
happening inside.
If not inside, we are saying that the reaction are happening outside and then imploding. It's not what we saw experimentally.
Yeah, because it's
Explode, they not implode.
No, but the reaction happens outside, and because of this explosion, it affects the whole thing.
Outside
it's not
of
going
this-
to simply stop the thing. So
I
it
think
happens
I
in
didn't
the
understood
surface,
very
in the
well this.
surface. It happens
The-
in the surface. There is not oxygen inside the thing
How
freely
so?
like this.
I disagree. I disagree on this point because we could see on the super slow motion videos that the sparks are actually liquid. So it's not there is not a surface around the spark. We can see they wobble. If
Sorry.
there was a solid surface, they wouldn't.
Is this
Explain more, please?
Is this sparkler you're showing the slide the same we used the previous ones?
These are videos from the literature with the same composition of the sparkles that we also got from the literature. That
And you
are the
said
conventional
that-
sparkles.
And you said that the sparks are molten. Does the opponent agree?
Yes, it's heated.
I mean,
And after all, but what we disagree here, the thing is two things. One, you said that it's expanding. We don't see sparkles, the sparks expanding here. Yes, it is molten, but you don't see it expanding. Here
can
in the
see-
first picture, you can see it expanding, but it's more because of the focus of the camera.
And is it molten in all the trajectory of the sparks, even after branching?
When they hit the ground, they will eventually cool out. But yes.
Because what I found in literature is that they stay molten for a certain distance, and after that, the branching can happen because they crack. So it's a solid sphere, and oxidation happens in the surface, and when the proportion of oxygen for the metal oxidating the surface is larger than a certain ratio, this layer can crack. So this is another mechanism other than gas expanding inside. I mean, it would be. I wonder if the opponent agrees if this other branching mechanism should be explored.
Okay.
Yeah, I agree. I agree with you.
Could you go to another point? I think I already
Yeah.
stated clear that it's not the case.
Yes, we can. There are several people with their hands raised. So, Lauro, you can go.
Hey, this discussion is interesting so far. Well, my question is to the opponent. What do you think about the development the reporter showed on the question in this statement, which asks for the determination of the maximum distance and also the size of the flame? Do you think what they show is reliable, is appropriately compared to the experimental data? How do you see that opponent?
I actually really liked his explanation of how far the sparks can go. I think that it's fitting. And although you said that there is no match, right, in the experimental settings, but they are calculating like how, in a hypothetical situation, how far it could go, right? So obviously this would be in a straight line. So there is not really the three-dimensional thing. I mean, straight line, it's a big-dimensional plane, right? Because it's going up. But either way, so I think this part specifically was actually very, very good. But I agree with you with the part of the size of the flame was lacking. And it's something we didn't realize at first, but after you mentioned it, we were like, oh, really? We missed that.
Now, Bernardo,
I agree with you there.
can go.
Hey, thank you. Can you go back to the slide number 25, please?
Yes.
About your experimental setup. I want to know, maybe this is your final experimental setup. You didn't make any change about it. And you said that your experimental setup was a good experiment, and I strongly disagree with you, because here we don't actually see anything to compare the size of the things, like a scalar. You could put a ruler over there.
That is the diameter of the Pieris. It's over here.
Okay, but the camera is extremely far away. We can actually properly identify the sparkles. The quality of the image is extremely low, and I don't think that with tracker you could trace all the sparkles properly. And you also have a 3D things. There is a way to constrain the movement of the sparkles to go in a plane. So when we're going looking the side view, we can like put a piece of paper and constrain the movement in one plane, and here in the upside view, again, we can also make
okay, thank you, but that was the reason that we recorded into camera planes, so we get all the angles information.
And you said you made over like 100 measurements. What were these measurements made at the same time? Because I don't think we could do it properly with this setup.
We do not have time for that, but I'd like to call again the presenting team to give their final remarks in 1 minute.
Okay, thank you. I think that both teams raised some really important and creative points about our presentation. I still disagree that they say that has a solid layer around the sparkler. We can clearly see that on the video that it's liquid. And also I disagree on the experimental setup. We're using the diameter of the Pieris and filming from up above. We could control the parallax really well and obtain important information. And I also would like to apologize if in the fight or in the presentation I was too fast. I was a bit nervous, to be honest, and the presentation has a lot of information, so I was a bit too assertive on the beginning. I tried to bust that after it, and I really loved our discussion. I think both teams did a really good job, and I would like to thank you everyone attention on this beautiful event.
All right, now we have 5 minutes for questions from the jury. So please, jury members, just raise your hands and you'll be allowed to ask. Who first is Claudio Lenz. You can ask a question. Go ahead.
Okay, well, very interesting discussion. Fantastic data, fantastic fitting, very nice. A question to all three. If I follow one spark and it branching, would I be able to solve this question whether the explosion is outside or whether the explosion is inside as the presenter is proposing by momentum conservation? So to all three of them in the order, presenter and then in the order.
Yes, I believe the observing one spark explosion, we can clearly see that the explosion happens from inside. And we actually did the conservation of momentum to various sparks. We have the velocity of it, and we can estimate the radius. And using the radius and density, we can get the mass of one spark, and we can write down the conservation of momentum. And we can clearly see that the branching.
I think just conservation of momentum is not really enough to determine the mechanism behind the explosion of the spark. But yeah, we would need to follow one spark and gather data on it to know really what's going on there.
My answer is a little bit different from the two previous ones. So because I also think that conservation of momentum is not enough, and I think other mechanisms should be taken into account because for the temperature change over time in the sparkler, for example, there is oxidation still occurring in the spark trajectory. There is energy loss due to thermal radiation, and also there is convection occurring. So you should take all these three phenomena into account and then solve some differential equation and see where the spark fades out, because in some limit, the temperature will be such that it won't glow the visible spectrum. So this is the approach I would take.
Okay, thank you. Now we move on to the next member, Matheus Farias. You can.
So my question is for the reporter team, but I would like to know also if the opponents and the reviewer teams agrees with the answer. So let's say now you are doing this experiment inside a small confined box, but large enough so that you can measure the further sparkle. How do you expect the sphere radius to change?
It's just for the reporter? Sorry?
The reporter.
Could you say again your question?
So let's say you are doing this experiment inside a small confined box, but large enough so that you can measure the furthest sparkle.
Okay.
How do you expect for the sphere radius that you determine, like the furthest distance, to change here?
Oh, actually, we define the size of the flame, the sphere, as the radius is equal to the average distance of the sparks, not the furthest. But if we define as the furthest, I think it would be not a very good parameter because we would have a lot of empty space inside the sphere that would define.
But how do you expect to change this sphere radius inside a small confined box?
Inside of, I think the volume of the sphere maybe would decrease. Actually, it depends on the parameters of the atmosphere inside the box, right? If you change the air inside it, clearly it would obviously change. But I think that mainly we have the consumption of the sparks oxidize in the air due to the oxygen, but I don't think there's a lot of oxygen.
Agrees with this explanation?
I didn't really understand the question. I'm a bit lost.
Okay, maybe let's move then. So people
can answer. I'm the reviewer. So.
Yeah, reviewer. Do you agree with the explanation?
No, I don't, because I think that if you assume that, actually I didn't understand by the reporter's answer if he assumed that your sphere was the way you define it, but assuming the sphere is the radius of the sphere is the farther spark. In the beginning, the sphere would be small because obviously the first spark trajectory is the farthest. But after some time, the sphere would be increasing its radius, and after a certain limit, I think it would reach a limit, and it wouldn't increase at all because it would be very improbable that it would pass a certain radius.
Other questions? Yeah.
All right, now Barbara can ask away. Yeah.
All right, so this is a question, and maybe I want the opponent and the reviewer to respond first, and then the reporter, whether he agrees with that. So both the opponent and the reviewer were pressing on the point that, so the problem was asking what the maximum distance is. And both the opponent and the reviewer were saying like, oh, the mechanism through which the sparks are branching is different from what the reporter is actually saying. So how is this different, and how would it affect the final result of their measurements, or the final result for the maximum distance that you're trying to measure?
Can I answer first? Well, I don't think that the mechanism in itself would vary the distance that the spark goes very farther, because it's not really what's being measured here, right? What we're being measured is how far it's going and the speed. So the mechanism in itself never plays a part on like how it's going to behave according to their explanation here, right? I mean, they do have the whole thing about air resistance, but it's not really related to the mechanism itself. So I don't think that this would change that much, but I think it's something important to determine. Sorry.
I think I disagree, because let's suppose, for example, that the spark doesn't branch. It will go to a certain distance. If the spark branches, it will break into smaller parts and also will release gas. So it will have a smaller mass after this branching. So it can go further because it will have a higher velocity, and also the temperature change would change inside each spark, so it can glow so it can glow longer than in the case that it doesn't range. So I think it's important to investigate this.
All right, thank you. So now, please, the next jury member can ask a question.
I think Barbara wants me to answer the question as well.
Okay. Do you, Barbara?
If he could briefly mention whether he agrees or disagrees that a different branching mechanism would affect the maximum distance that it's achieving.
So I think depending on the mechanism, could affect, like they said, they were saying the explosion was happening from outside. So if the spark imploded, this could significantly change the energy and the velocity the children of the spark can go. But overall, if we consider an internal explosion, I don't think it would change that much. Besides the energy.
All right, thank you. Now, Professor Alexandre, please, if you could ask a question, a brief question, just
Okay.
I hope it's brief.
Actually, I'll keep on this point. Actually, Barbara already started this question. So if you look at this graph, like the graph that is on, there's a difference between whatever was measured and the maximum distance that was achieved. And I wanted to hear from all the teams whether you think this is a lack of statistics, so lack of number of measurements, or whether the point that was raised really does actually have an impact on this maximum distance. And I think you could actually go back to what Claudio was asking about conservation of momentum, maybe to answer this question.
Do you want me to answer first?
Yep, any order you prefer.
Okay, let's remind us that this is the maximum distance, and you can clearly see that none of the distance measures are greater than the maximum distance. And I want to remind that the maximum distance is a very low probability. Even it's a zero probability event. So all branches happen in the same plane, and it happens the maximum number of branches, the maximum number of lifetime. So it's a theoretical question that we can't really see an experimental relation, but we can see that we have just centimeters apart. So I think it's coherent. It's not meters, they are centimeters. So thank you. This is my answer. They're the same order.
I actually
the same order.
Sorry.
No, I am done. Sorry.
Okay. No, I actually agree with his answer. The conservation of momentum thing. I think that's basically what they did, right? And the main point here is that it is a theoretical question, and the event that they calculated, it's very low likely to happen. So the data is correct. We could try to find out what is the how to say, most distance measured, right? But aside from that, I don't see much of a point. I finished.
Okay. So I think we're all done then with the question time. So I would like to ask our jury members to write down their grades on the forms that we've sent to them. So please put your grades on. And just another comment as well. We're not going to be giving comments right now on the grades. Only at the end, we're going to give space for the jury members to comment on all presentations. Okay. Okay, we're still waiting for the grades. And if you're watching us through YouTube and you're from a university that's not one of the four that are competing here, we would like to encourage you to form a team to participate in an active Brazilian Physicists tournament. Yeah. Hopefully next year you'll be here with us, and hopefully in person too. It would be pretty cool. If you like the fights right now, I mean, if you see them live, you're going to be really happy, you know, because they're really cool. Can also be some, you know, kind of sad sometimes, but you know, it's life. Just kidding, but you know. Right, just a few grades missing now only. All right, so we've got our grades. We're not going to give space for comments right now. So we would just like to thank you all for this really cool fights. And once again, I will just share, briefly share an image here. And we're going to have a 5-minute recess again. Okay, so please, let's have 5 minutes. And we'll see you again soon for the third round of this final physics fight in the Brazilian Physicists tournament. Mas aí, para entreter o pessoal aí do YouTube, né? Henrique, você não tem uma musiquinha aí legal, não, que a gente achou, pô? Porque eu tava metendo uma música aqui ontem, e aí o que aconteceu? Eu tava falando, não, porque vão tirar do ar o vídeo e tal, mas eu falei, poxa, mas é bom ter uma musiquinha, né? Aconchegante. Enfim, vou mostrar a imagem, Henrique. Calma, já estamos aqui.
Coloca a Tim Maia de novo, Matheus.
Ah, queria, né? Mas aí o pessoal já vem com o painel que vai dar strike, não sei o quê. Hein? Aí eu falei, pô, mas queria, né? Queria. Por mim, a gente tava aqui cantando que beleza. Mas vou fazer o quê? Ah, não era esse slide não, esse aqui é outro slide. Deixa eu achar a minha imagem aqui. Bom, o importante
aí o cara mostra o slide da equipe vencedora já.
Não tem não.
Nada roubado.
Que é isso?
Tô brincando.
Não, mas o BPT aqui não é bagunça, não. Cadê? Eu tô tentando copiar a imagem aqui. Vou deixar aqui com a ordem das coisas. Enfim, vou deixar aí uma apresentação geral de slides aí, que o pessoal pode acompanhar depois também. Um salve aí pro pessoal no chat do YouTube, salve para minha mãe que está assistindo agora aqui, ó, tá falando, o microfone tá aberto, mas eu sei que está aberto. Isso é entretenimento para a equipe não, pro pessoal aí do YouTube, né? Só não tem a musiquinha, Henrique, cadê a musiquinha? Tô esperando. Mas enfim, temos aí uma bela apresentação de slides, contando um pouquinho da história do BPT, do IPT, do Brasil. Aí algumas imagens, né, da equipe da Unicamp. Eu não sei de quando que é, acho que é de 2019, 2018. Essa imagem de cima eu sei que é do primeiro do primeiro BPT que a gente teve. Já tem história já, né? Olha só, gente. Estamos chegando ano que vem já é 5ª edição. Imagina. Aí, ó, o pessoal comendo uma pizza. Pô, não faz comigo não, cara. Tô com fome aqui. Aí, ó, foi a final, né? A final do ano passado, que a Campo ficou em segundo. Do coisa. Esse foi o nosso primeiro BPT, lá na UFABC. Esse auditório lindo. Pô, imagina que maravilha, né? Você apresentar num slide tão grande assim, seus resultados. Tem que ser esperto, tem que ser corajoso para apresentar resultado grande assim, né? Porque a pessoa consegue ver tudo no slide. Não adianta colocar erro de.
Matheus, ninguém tá vendo slide nenhum, não.
Sério? Que isso? Não acredito. O que vocês. Eu tô falando 10 minutos aqui. Pô,
Cara,
gente,
você descreve tão bem as coisas que eu conseguia ver, entendeu? Sem nem.
Pelo amor de Deus,
A
que
didática
droga.
é impecável, tem como não.
Meu Deus do céu. Mas enfim. Jesus amado, hein? Eu aqui falando sozinho, pô. Pô, tem 27 pessoas na ligação. Enfim, tudo bem, mas o pessoal se entreteu. Então, enfim, aí, ó, imagens da Unicamp. Aí naquele ano, aí, ó, o pessoal comendo pizza. Vocês viram, né? Gostaram da descrição das imagens. Pior que, deixa eu ver, alguém me mandou mensagem aqui. Acho que não está transmitindo nada, tá? É verdade, não estava mesmo, de fato. Mas, enfim, é a vida, né? Isso aí, ó, ficou na Unicamp, ficou em segundo ano passado. Tava tão animado aqui, né? Porque, assim, eu pedi até pra moça fazer. Eu falei, não, faz aí os slides, né? Pra Mariana aí da organização também, que ajudou a gente. E aí, acabou que, enfim, eu tava só narrando e não explicando nada. Mas aí, ó, é isso que eu falei. Esse auditório grande, ó, você tem que ser muito corajoso para apresentar seus slides aí, entendeu? Porque você consegue ver a barra de erro direitinho, tudo. Você consegue ver tudo. Aí o pessoal da USP, olha só, olha a alegria, olha a felicidade que o IPT traz para as pessoas, gente. Você não vê uma pessoa chorando nessas fotos. Aí, né? Porque eu, por exemplo...
Chorou depois.
Exatamente, também tem isso. Aí isso aí, ó, o pessoal da USP esse ano, aí o Bruno, Lauro, o Matheus. Aí ali, ó, no fundo, ali embaixo era o BPT que a gente teve. Essa foto aí de cima foi no BPT que a gente fez lá em 2019, né? Acho que foi 2019, enfim. 2018 pro 2019. Aí, ó, o pessoal da USP também, ó, o pessoal desde o primeiro ano aí, sempre, cara, participando bastante, pô, muito legal. É isso, temos várias imagens aí interessantes. Você lembra, era tudo vazio antes, ó, não tinha quase ninguém. Agora, tá tendo mais gente, pô, ia ser muito legal ter todo mundo aí discutindo também os problemas. Enfim, vários apresentadores. Enfim, vamos... Bom, acho que já deu tempo.
Todo mundo aqui?
So let's see. I think that
sim.
Now we switch to English again. So let's see. Barbara is here. Alexandre is here. Matheus Farias, I believe, is not here yet. Apparently, I don't know. Let's see. So in this round, we're gonna have the team from the Federal University of ABC being the reporter. The opponent will be the team from Unicamp. The reviewer will be the team from the Federal University of Minas Gerais, and the University of São Paulo will be the observer. Okay, so let me just check once again if everybody's here. So Alexandre is here. Blah, blah. Oh, Claudio Lenz, I don't know if he's there yet already. Let's see. Oh, he's there. Okay. So we have 3 jury members at least. Let's see who else is a team, who else is a jury? Claudio Lenz, Alexandre. Oh, Edward. Edward, are you there already? Not yet. See, so that's why it's important for us to wait a little bit longer. So Edward, Claudio Lenz, well, There's one missing, I think. Let's see. Oh, Matheus Farias also. Yeah, we're also waiting for him. So. Okay, Claudio Lanzanos is there, but we're only waiting now, I think, for Matheus Farias and oh yeah, Claudio Lanz is there with some coffee. I see. Nice. Now we're just waiting for Matheus.
And some snack. I can do that, right?
No, of course, yeah, no. You're encouraged to take snacks. So
yeah.
Please, one day we're gonna have snacks to provide. Hopefully, we're gonna be, sponsored by, I don't know, some snack company.
And too.
Then you could send. People are doing that. You could ship to the jury and people.
Yeah, imagine all jury members get an Uber Eats.
Yeah, exactly.
That would be nice. Yeah, one day.
You can get Itaú.
I mean, you guys did have me at breakfast time at 7 a.m. and then at lunchtime at noon. So
see, yeah. We're still waiting for Edward and Matheus Farias, I think. So please give signs of life. Oh, Edward is there. Okay. And Matheus Farias, are you there? Oh, with coffee. Okay, Edward is also fueled by coffee. Nice. Well, okay. I mean, we're just going to wait for Matheus and let's see.
Yeah, just a comment on the fight. This 2 fights ago was that instead of using sand, the Minas Gerais could have used ground coffee.
Yeah, you even wrote that on the chat for us too.
Yeah, and you can get ground coffee at different sizes and so on.
That would be a waste of coffee.
Well, of course, but I mean, you could get.
No, that's a sin. There's no discussion.
No.
All right.
You would use a tiny bit of what you would get from the companies, right? So,
Yes, they could send the disposable ones, the ones they're gonna throw in the trash anyways, and then that's not a sin.
All right. So I think we're all here. Now I'd just like to confirm if all team members are here as well. So the teams from USP, Unicamp, UFMG, and who else?
Unicamp is all here.
Right. Yeah. Okay, so Unicamp is all here. UFMG, are you also there?
Yes, we're here.
Cool. So now UFABC, are you there? You're going to be the presenter. So
Yes.
cool. And now I'm missing. Oh, USP will just be the observer, but it's nice to have you all here too if you're around. Okay, so I believe we can start the period then. And so the presenting team will be UFABC, and you have 3 minutes to prepare your presentation. You can start this presentation time right now. I can even read the statement of the problem, I think, while we have this
Oh,
time.
sorry, I was muted. Oh, you can.
Oh, yeah, sure. Like just so we have some time to kill. So chaotic magnetic pendulum. Consider a pendulum consisting of a magnetic bob attached to a string. If the pendulum is allowed to swing over a structure of permanent magnets, it will display complex motion. Study the pendulum dynamics and its dependence on the number of permanent magnets and their arrangement. So that's the question. I think it's a cool effect.
Can you show the video?
Oh, sure. Sorry, I can also. Yeah.
I think it's
for the sake of it. So it's easier for people to visualize.
Yes.
Yeah. So this is the effect that will be studied by the team. So yeah, you have your minutes there for a presentation.
Okay.
It's a pretty interesting problem. Yeah.
I'm ready to present.
Oh yeah. So please, Enrique, just give him the permission to present.
Okay. I'm co-host now. Let me share my screen. Okay. Can
Still have
everyone
some
see my
minutes
screen?
there. It's loading still. All right, now we can see. Try changing the slides just for us to see if it's going. Yes, it's working. So, all right, if you're ready, are you ready?
I'm ready.
Okay, so the team from the Federal University of ABC has 12 minutes to present, starting right now.
Hello, everyone. My name is Lucas, and I'm going to be reporting problem number 13, the chaotic magnetic pendulum. The problem statement, we just saw it, but it's basically a string with a magnetic bob on its end, swinging freely over a configuration of permanent magnets. So I would like to begin with a very simple definition of chaos. What we think about when we think about chaos in everyday language, it's related to messiness and lack of order, and something that's generally out of our control. But there's much more to it in science. Many mathematicians define it as being easy to spot but hard to define, and there's no accepted universal mathematical definition of chaos. But there are main characteristics of chaos that help us determine a system is chaotic. It's a complex behavior emerging from simple rules. It has a high sensitivity to initial conditions, and it's generally not random. There is random chaos, but generally it's not. A very nice sentence that exemplifies two of these three characteristics is read as chaos. When the present determines the future, but the approximate present does not approximately determines the future. It's a sentence by Edward Lawrence, the father of chaos theory. This is the Lorentz attractor, one of the first systems, if not the first chaotic system to be studied in history, and it's given by these three simple equations, three simple rules. We have as example of chaos other two instances. Well, there are many, but I showed only two. This is a fluid going through a cylinder, and it generates this very nice von Karman vortex. It's a chaotic system. And this Mandelbrot set of power 5, it's also a very beautiful system. So the chaotic pendulum has been around for a long time, mostly as a toy. There's this 1994 booklet by NASA called Toys in Space, which they already knew the problem, they already studied it, and they considered using it in space for involving children in STEM fields. They obviously didn't do it because there's no gravitational field. It really messes the system. But even nowadays, we have this very nice toy that's commercializable, and you actually have one in the lab. It's pretty nice. What is there in the literature? Lots of theory, and there's a couple of models they use, and loads of simulation. But there's not much experimentally about this specific problem, and that's what we wanted to tackle. With the simpler problem to model our system, which is a spherical pendulum. And it's kind of a simple pendulum that's allowed to swing freely over a spherical shell, but it has other components. So it doesn't just go front and back. It goes towards all directions. And then we complicate it a little bit, adding magnets. So what it's going to do, it's going to add this potential wells to, oh, I'm sorry. Is it okay? This potential wells to the system, and this varies drastically the trajectory that the pendulum is going to swing over. This is a attractive basin, and this is repulsive basin. So I'll talk a little bit about our setup. It's a 2 degrees of freedom gimbal, consisting of an outer gimbal and an inner gimbal with a sensor to capture data. As you can see, this is a sketch of the system. You have a rigid rod here and a magnet. The reason why we use a rigid rod instead of a string, as the problem proposes, is because the string would add torsion, another degree of freedom to the system that we wanted to avoid. So the problem state statement itself doesn't use we have 1 magnet, 2 magnets, and 3 magnets in these following arrangements, and all of them were in attractive mode. This is a picture of the setup. As you can see, the gimbal, outer gimbal, inner gimbal, and bearings here to allow it to freely swing over the axis. And we have a rigid rod here with a magnet on the tip. There are a couple of videos here also that I'm not going to be showing, but they are interesting because they have a nicer frame of what's going on. Unfortunately, I'm not going to be able to show, but it's not okay. Maybe I will. Okay, it's not important. So we had an action very important to the system. It has two different friction components. For each axis, it has, and there are actually two mechanisms that add friction to the system: air resistance and dry friction. So the dry friction is given by the bearings, and the air resistance by the whole system, the outer gimbal, inner gimbal, and the rigid rod. This is a curve fitting we did to show that this is a suitable model. This is the amplitude of one axis falling through time. And we did this analysis to both axes, and we fitted a model for dry friction and air friction. And as you can see, it's pretty good fit. The sensor we use is an MPU 6050. It's an accelerometer with a gyroscope. It measures angular displacements and angular velocities and accelerations. It's a pretty great sensor. These are its data sheet and the uncertainties we get from the data sheet. So a nice way to analyze the system, the dynamics of the system, is look into its phase space. The phase space can tell us a lot of information. One of them is how the trajectory is moving. So as you can see here on the outer shell, we have a lot of energy. And so this is no magnet, so it's going to follow a very simple trajectory. It's going towards the middle because it's losing energy to friction. So the radius of the trajectory decreases in time. More interesting is when we add magnets. So you can see this is the high energy state, and it doesn't feel the magnet so well. So whenever it gets closer to the center, it starts to feel the magnet, and it accelerates towards the center of the magnet. With two magnets, we have a very similar yet different trajectory. And with three magnets, we have this much more complex behavior going on here. However, it's a little difficult to visualize what's going on with the motion with phase spaces, so we prepared something else. We have a 3D model in Blender of the system. This is a one-to-one model we made, and the nice thing about Blender, it's scriptable in Python, and it accepts quaternion data, which is what we captured with the sensor. So we can actually make a nice path simulation. It's not simulation. It's important to notice this is a video from real data collected, and it's sped up by 1.5 speed so that it won't take very long. But it's a great video to visualize the dynamics. This is with 3 magnets. Oh, okay. So as you can see, in the beginning, it doesn't feel the magnet very well because it's still with a lot of energy. But as it's losing energy to friction, it starts feeling the magnets better. It starts to fall under their magnetic potential. So as you can see, it starts really feeling the sense that there's a magnet there. And well, I guess the trajectory speaks for itself in this case. It's losing more and more energy, and it starts to feel the other potentials. And this is why the system is considered chaotic, because you can't really know beforehand to which basin it's gonna fall under. If you may make your predictions. I don't think that the result is too intuitive. Well, in this fight, gravity won. So that's the system. And a question that may arise is there an objective measurement of chaos? And yes, there is. It's called Lyapunov exponent. It's a great way to classify if a system is chaotic. And the thing about the Lyapunov exponent is that it takes a lot of data. I'm talking about tens of thousands to millions of different measurements from the system. That's not something that we can easily gather. However, there is another kind of Lyapunov exponent called the local finite time largest Lyapunov exponent. This is something that we can calculate with the amount of data we have. And there's this Rosenzweig's algorithm, which actually makes this calculation from a reasonable amount of data. However, the data that we had was not enough for it because there's still a lot of friction in the system, so we didn't have enough data points to make it. This is something that can be easily fixed with a better setup, and this is in our conclusions. We have collected tons of data and empirically explored differences in phase space of systems with different configuration of magnets. And in order to have data well suited to calculate the local finite time largest Lyapunov exponents and conclude objectively whether each configuration is chaotic, we will need tons more data and enhance our setup. And also that friction plays a very important role and should be fine-tuned to yield the best result. That is, if the friction is very little, we wouldn't feel the magnet for a long time. And if the friction was too great, the system would just collapse very quickly. So fine-tuned friction would be ideal for this problem. And that concludes my presentation. Thank you.
All right. Now we have 2 minutes for technical questions from the opponent team. Please go ahead.
Oh, thank you. First, at slide 8, please. What are the figures that you showed us from the literature? What does they mean?
Okay, I'll go back there. So yes, that's actually very interesting. I didn't want to go into that because I didn't do that simulation in my paper, in my presentation, but it's really interesting. What it does is each color represents that the system ended up in a different magnet. So for instance, blue means that the system ended up in this magnet, gray in this magnet, and red in this magnet. And
I think I got
each
it.
pixel mean initial condition. Okay.
Thank you. Slide 10, please. I'm sorry to pressure you, but I have little time.
Okay.
This force is proportional to what? This potential that you...
There are two models in theory. They use inverse square as an approximation, but the more accurate model is inverse fourth of as a force. The magnetic force is proportional to the inverse fourth of the distance between the magnets.
Okay, and go on this line where you showed 3 phase space, please. 3 graphs of the phase space.
Yes.
Yes, this one. These are different initial positions, right?
Yes.
And they all converge to the same magnet?
I believe these two do, but this one doesn't. This one goes to another one.
Okay. Is there a reason that you choose to plot the y-axis on the vertical axis on this phase and x on others, or no?
Yes, the phase space is consistent of two. Well, it's a 4D plot actually. It's two velocity components and two position components. And if I were to plot the two together, it would be very crumbled. So I plotted the one that happened most things in it, as to speak.
Thank you.
All right. So now the opponent team has 3 minutes to prepare. 15 seconds.
I'm now able to start sharing my screen.
Oh yeah, you have to allow Leonardo to share the screen, Henrique.
Let me try. Yes, I can.
Okay.
I believe you can see now.
Yes, yes.
Some spoilers.
All right. So you have 5 minutes to present. Go ahead.
Okay. Thank you. Hey guys, I'm Leonardo Falabella, and I will do the deposition for the magnetic pendulum. So firstly, let's remember the problem statement. It asks us to consider a pendulum that swings over arrangement of different magnets, and to study the pendulum dynamics and its dependence on the number of permanent magnets and their arrangement. So I will start for the strong points on the reporter's presentation. Firstly, they identified the main chaos properties that are that everyone agrees upon, and they gave some examples of chaotic systems, which are interesting. They cited theoretical literature on the problem, and they also showed a plot on the magnetic potential that was helpful to understand how the magnets interact. They showed a creative experimental setup using an electronic device to track the trajectory of the pendulum, which is pretty helpful to get great data, and it's easy to make a lot of repetition and have statistical measurements. And they also calculated the friction coefficients of their setup. So we can see that they were worried about the precision of their data. However, now I'd like to point out some maybe improvements that we could suggest for them. Firstly is the imprecise magnetic potential, just because what I asked about on the technical questions, they just showed an image without much a scale. So I would appreciate a formula or something like that for the magnetic potential. And we think that they could explore the Lyapunov exponents. They gave a reason of why they didn't. However, we think it's still possible to get somewhat idea of what are the Lyapunov exponents of this system. They lack a theoretical model for the magnetic force strength and even the trajectory of the pendulum. They cite that the theory that the literature explained this, but they just said that, didn't explore it or showed how it goes. They have some imprecise experiment conditions. Their initial condition on their trajectories are kind of loose, and I couldn't understand clearly how they did it and what are the force of the magnets that they used. He showed the video that the magnet was pretty, didn't even notice the magnets on the beginning of the trajectory, and that it would change with different magnets. So why don't maybe try to with strong magnets? And they offered some confusion about the deterministic chaos as well, because he said on the presentation that with an initial position, you can know where the pendulum will end, and that's not that simple, but we can discuss this later. So some points of discussion. He didn't explain if this system is clearly chaotic or not. I would like to speak about the Lyapunov exponents. How would he build a model since it is available on the literature? Why he didn't explore more condition or made more trajectories on his experiments, since he has a very good setup? What is the influence of varying friction, which is a pretty important factor in my opinion on this problem? And how would a repelling magnet change the phenomena? How would the arrangement of magnets affect it? If you have an irregular polygon, for example, not a simple regular polygon on the origin, that was more what he explored. And finally, did they solve the problem? We believe that they just partially solved it because they explored some aspects of the system. However, they didn't clearly show that this system is chaotic and didn't explore couldn't explore much different arrangements of the system, and didn't show as well a theoretical model to try to predict the trajectory. I conclude my presentation, and I'd like to invite the presenters team for the discussion. If he can share his screen, please. That would be nice.
Thank you, Leonardo. It was you raised some very interesting points, and I'm very glad to talk about them.
Oh yes, please. I'd like to start by questioning you about if you consider the system chaotic and why. Can you show this for us?
Okay, I'll begin with this then. So this system is a system that's still being studied nowadays, and there's a fairly recent paper from 2013 that talks about this being a different regime of chaos. This is not the classical chaos we are used to. It's called doubly transient chaos. And
okay, but sorry to interrupt you. You have a pretty a good definition of chaos on the initial of your presentation, like 3 properties that the system must have to be considered chaotic.
This still follows the 3 definitions. It doesn't go away from it. It's just the way that the system is studied is different from the way that classical chaotic systems are studied.
Okay, can you show this for us and prove that this is the case?
So this is basically the whole point of this paper. And the part that we have is that usually when chaotic pendulum is studied, it's a driven chaotic pendulum. Because this is not a driven chaotic pendulum can go on forever, even with friction. And so you can have a kind of infinite time Lyapunov exponents.
Okay, maybe I'm sorry to interrupt. I have more points to cover, but my question, I believe, was pretty straightforward. I think you're a little deviating, so I will move on. That's okay?
Okay.
I'll touch upon the Lyapunov exponents. You showed 3 trajectories on the phase space, and I would ask you, why don't just calculate the Lyapunov of that 3 trajectories?
I have calculated the Lyapunov exponents for the 3 trajectories, but it was really inconclusive. Each time the algorithm was being applied, it was given different results, which I don't fully understand why. If you want, I can send you the paper that calculates it.
That's actually the normal behavior of Lyapunov exponent. A chaotic system have, as you said, to determine the total Lyapunov exponent of a full system, you have to have a lot of data. That's, I believe, what you meant on your one of your last slides. However, you can calculate the Lyapunov exponent from 2 trajectories, and if they deviate, that's a sign of chaos at least.
This particular algorithm calculates the Lyapunov exponent from 1 single trajectory. It applies a delay to each point, and then it kind of simulates 2 different trajectories.
Yeah, that's my point. I would like to touch upon now. What do you think is the friction role on this problem? What will happen if we got to like our 0 friction regime?
I believe if we had a 0 friction regime, we wouldn't have very interesting dynamics going on, because it would be as if we were approximating. So it depends on the parameters of the problem, but the way we were working on it, the way our setup was set up, it would be as if the magnets were non-existent. It would be like we were approximating the potential to be 0 of the magnets.
Okay, that's don't seem the case for me, because if you have a low energy state, the potential would be visible for the still be visible for the magnet, and
I mean, if
we
you
will
drop
still
it
have a
very
chaotic
close to the
system.
magnets, then probably yes.
Oh, but not even close. If you have just strong enough magnets to affect the trajectory of the pendulum, you would have the pendulum with the same energy all during the interval time of the movement, and we would have chaotic trajectories.
Yes. Okay.
Oh, I see. And why didn't you show for us some model that you could try to predict some trajectories or something like that? I believe that would be an important point for the presentation.
I actually haven't applied the model to the system. I used a guide to understand physics of what was happening.
Oh, I see.
All right, thank you very much. Now we move on from 2 minutes of technical questions from the reviewer to the opponent and to the presenting teams. Starting now.
Hi, can you hear me properly?
Yeah.
Yes.
Okay. I'd like to ask in this slide number 22, you when you were modeling, you use the same dimensions of the system that you have in your setup, right?
Yes.
So you know the dimensions of the rod, the distance between the. Okay, thanks. In the simulation, do you know if it's not your simulation, but do you know if they consider any type of dissipation from this?
Yes, friction is a very important part of this problem. There are some simulations in literature that you can. It's not in actually literature. There are some simulations they did with Mathematica that we can vary the friction coefficient, and you can see if you make it 0 in most configurations, it doesn't get too affected by the magnets. But like this pattern is not formed. This fractal pattern is not formed.
Okay, thank you. Can you go to slide number 9 for a second?
Yes.
Okay, this is just a simple pendulum, spherical pendulum, right?
Yes.
Oh, okay. And that's all from my part.
Okay.
All right. So now there's one minute for preparation of the reviewer. "15 seconds. Who's going to present also so that we can give the permission? Give the permission.
Oh, it's me, Bernardo.
Okay, Bernardo. Okay, nice. So please allow Bernardo to share.
I'd like to ask for a technical timeout, if possible,
Okay,
please.
cool. Yes.
Okay, thank you.
Yeah, I think you already have the permission, so try to share there.
Okay. So 1 second. I'm trying to share right now.
Okay.
Is it appearing for you?
No.
No. Weird. What about now?
Yes, now it's going. So the reviewer has 3 minutes to present, starting now. Yay, you can go.
Okay, thank you. I'm reviewing the problem chaotic magnetic pendulum. This is the statement of the problem. And first, I wanted to point some good points in the reporter. This presentation was pretty good. It shows the definition of the chaos, what a chaotic system is. It is an extremely important term that we have well established before diving right into this content. So point for them. It was a good, extremely good experimental setup. We got to admit it, and it's extremely clever way to collect the data. He also explained why they used a rigid rod instead of a string, because the problem statement stated that the problem magnetic should be made with a string, and they used a rod, and they explained why they did it. They also had a Blender animation. They have a Blender model and a Blender simulation. The simulation is not theirs, but they have a model. They could have animated that. So it was good for them. So some aspects to improve, I found something strange in page 16, which it's not clear what is the difference between the data collected and the feeds. Lack of controllability of the initial conditions of the system, because it is in the definition of the chaos, but they didn't control that very well with the setup. And the problem states that they wanted the dependence on the dependence on the number of the magnets and their arrangements. They only made 3 experiments, and I don't think that matched very well this statement. They also didn't explain properly where the chaos is in their system. And for the opponent team, they made extremely good points about the chaos. They also wanted explanation of the upload exponents, because it's important wasn't very explained in the presentation. They also present very relevant questions about the model of the magnetic force, the dipole in the system. But in aspects they could have improved, like they could have asked about the rod dimensions and the vibrations interference in the system. They also failed to mention that the group did not answer actually this shouldn't be here. They noticed. Sorry. But I wanted to determine that they talked about the initial conditions, but they could have discussed a little bit more about this in this system, because this is an important fact in a chaotic system, and they didn't elaborate enough about what the proper how these affected the problem. The point we wanted to discuss is what is the magnets? What if the magnets are attracting instead of repelling? Would the system evolve the chaos? And how does the rod dimensions affect the route to chaos? And the chaos happen for every magnet combinations. If not, for what magnets arrangement can we observe for the chaotic behavior?
All right, you can start the discussion already.
Would you like to share your screen?
Can we leave that? Oh, okay. I'll share my screen.
Sure.
Sorry.
To start reviewer.
Thank you, Bernardo. Do you want to start, Bernardo?
I'm sorry. You can start UFABC.
Okay. So
I think I'm sorry. I think you should start by talking about the arrangement of magnets. Do you agree with you?
Yes, we actually like that aspect. We did not analyze the arrangement. We didn't change that many variables.
Oh.
Yes, that was a lack of our experimental setup or
But
the
you,
way
you
we
agree
did
it would
experiments.
be, sorry, you agree that it would be an important thing to.
Yes, it's definitely important to the problem statement itself. Yes.
Yeah, it's
Do you
explicit
agree,
says it, right?
Yes, yes, yes. That's right.
So, how do you think a repelling magnet would affect the phenomenon? Like, if you have the triangle that you is showing, if the top one was repelling, how do you think the trajectory would change?
So we would definitely go away from here. So we would be competing between these two magnets. All I'm gonna say about this, the different configuration is about memory of experiments we did early on before setting to the setup. So it would be the whole trajectory would focus around these two magnets.
Yeah,
And
but could you
compete
tell
between the gravitational well and so you can say go ahead.
I'll just try to say, could you test this with the experiments that you showed on your presentation?
You mean like the
phase
model?
spaces.
Like with what?
The
phase space?
trajectories. Yeah,
yes,
if
I had the experimental data, I could definitely make a phase space.
Yeah, that's I believe a main point of concern from your presentation, because if you just launched the pendulum from one isolated initial conditions, you can really have a very deep understanding of what's happening on the problem. I would suggest you to try to make what the literature made on that you cite about, so the basis of attraction map. You could really see what would change on the different initial conditions for each arrangement of magnets.
Yes, definitely. That's a great point. We should make a setup which could allow us to finally control the initial conditions, so we could be as close as possible to initial conditions. Try to make them the same, because they're never going to be the same, and that would be a great way to settle two different initial conditions.
Okay, I'd like to ask a question for both opposition and reporter. You can stay in this slide. Can you tell me where do I see that this system is a chaotic system? Just looking in the phase space, like this image show properly how this system is actually a chaotic system, and when does the system start a chaotic movement? Just looking by this image in the phase space.
Right. All team members can also join the discussion now.
You can start. I don't know who would like to start.
I'd like to start.
Go ahead.
I don't think so. You need at least two very close trajectories to try to make an initial guess if the system is chaotic or not.
That's a great point, but I think we could extract something from this data alone, which is if you notice the z-axis shows us the y position. As you can see, it wobbles around a lot around a different y positions whenever it really feels attraction from the magnet. So what this can suggest us is that it could have fell under any of these three different configuration of magnets, because it takes a while to settle to a point. So it could have been on the second, on the third, and I think this by itself already shows some suggestion to chaotic behavior.
Do you agree with him, Unicamp?
No, I disagree. As I said it already.
Okay. So, Álvaro, your hands raised. You can say something.
I'd like to comment on a point that the reviewer raised, and I think it's really important to the problem.
Okay.
Since you discussed if it is chaotic or not, and we know that chaos depends on the initial conditions. How did you control your initial conditions?
I didn't. That's a fairly reasonable point of why our experimental is lacking, because that
Okay.
is said explicitly in the problem statement, and we could have done a better job doing that.
Yeah, I agree with you. Thank you.
Okay, so another point that we could discuss is the dependence of the rod. Like not dependence of the rod, dependence of the number of the magnets. Did anyone here found in defense of the number of the rods? How many rods? Sorry. How many magnets do we need in the system to start a chaotic system?
Maybe the reporter could start.
Okay, so talking to a professor who's specialist in chaos, but theoretical, he says that 3 is the magical number. The thing is, further experiments on this setup, we're still gonna make more data with this. With further experiments, we could prove or disprove that. We could make like, say, what is the drawing line? Where do we draw the line? 1 magnet, 2 magnets, 3 magnets, changing their arrangement and changing their repulsion and traction, because we don't have conclusive data.
I would say 1 repulsing magnet or 2 attracting that clearly makes a double L potential.
My intuition would say the same, but I'm not sure.
Okay, fair enough.
Can I add something?
Okay, sure. Sorry, I didn't see your.
Yeah, no problem. Yeah, so the reason we did not perform the experiments as you all suggested is that the main problem of our setup is that the friction is not uniform around the 2 axes. So our main concern was to try to reduce and get the most the most equal value we could achieve, right? So that was the main part of our experimental technique.
I don't think that's really a problem.
Okay, that was it. So now we have the concluding remarks from the presenting team. You have 1 minute.
Okay, both things raise extremely valid and very important questions, and I believe they're mostly correct in most of their assessments. We truly do need to make more measurements that are more conclusive and work on our models better to have a theoretical valid method model and to confirm that it is valid. I think this problem has a lot of interest to the continuation of the science on this problem, because we don't see lots of experimental data on this problem itself. And I think it's really interesting to keep following this project, to make it a long-term project. So yes, I think that's it.
Yeah, cool. Now we move on for questions of the jury. So please, Claudio Lenz, raise his hand first. Go ahead.
Okay, I have a suggestion and a question. Suggestion for the reporter is to implement a little electromagnet where you can fix the initial position, switch off the current immediately. And with that, you should set your initial conditions really well, because you can move this electromagnet. The question for all of you, from his picture of his pendulum, it seemed like the whole mass of the pendulum, I mean, in the bottom of the pendulum was the little magnet. So my question is, if he put extra mass on that end, would it affect the role of friction, for instance, as you're giving more energy to the system? So it's a question in the order. I'd like the presenter and then the opponent and then the reviewer to answer. What would you guys expect?
We made a lot of
go around friction by using this method.
We worked with a lot of setups, and our first setups was a string with a very massive ball on its end, and steel ball. And what we experienced is the more inertia the system has, the least interesting is the system. The longer it takes for the magnets to affect the system. So I don't think that would be very interesting to study the problem. In fact, we would like to reduce the mass of the rigid rod we have. But regarding friction, I'm not really sure how to answer that. I really don't know. Maybe it would increase a little bit of air resistance because of the size of the sphere, but I'm not sure.
Oh, I meant the role of friction compared to the other terms in the equation. You know?
Oh, okay. Maybe it will be lesser because of this inertia.
Yeah, with a larger mass on the pendulum, you do have a less effect of the friction. You'd see less. If you fine tune the magnets with a strong magnets, I think it would be okay. But the main role that the friction does to the system is that it makes it a lot harder to predict where the pendulum will end, because you have it kind of increases the chaotic the chaos of the system. I'm doing this because chaos is not a quantitative measurement, but I think you can get what I mean.
All right, then I can take one. Oh, wait. Oh,
sorry. I'll be brief. I strongly agree with the team. We increase the mass of the system, then we will observe. It will be actually even harder to get the chaos, because we had a simulation we made from scratch from a chaotic magnetic system, and we could vary the parameters very precisely as we wanted, the mass, the system, rod. And when we increased the mass of the system, we observed that the system would get a longer time to achieve the chaos. And also it would, by the second law of Newton, the increasing of the mass would implies that we need the acceleration would be it would be harder to change the momentum.
Okay. Thank you. I think we can move on to next question by Matheus Farias.
So my question is just for the opponent team. In the discussion, you mentioned that it's interesting to analyze this problem without friction. So let's do it now. Let's say you don't have friction and your initial condition, like the amplitude, is small enough so that you can perceive the magnetic force. How do you expect to change the phase space plot? You can make all the assumptions you want to simplify the problem.
You mean just one magnet attracting the pendulum and the pendulum swinging?
Let's say 3 magnets.
Okay. I don't know what do you mean by small oscillations. Is that what you mean?
Your initial condition is not so high, the amplitude is small, so that you can perceive the
if the pendulum is interacting with all 3 magnets, you wouldn't have the converging of the pendulum to a single magnet. It would just keep on with a crazy trajectory. And this would be a very important case where the Lyapunov exponent would be a great measurement of the chaos of the system.
All right. I think we can move on then to the next jury member. Please, Alexandre, go ahead.
So imagine that you could improve on your initial conditions, and imagine that you have a very good description of your magnetic potential. If you come up with a model to do a simulation of your movement, how well do you think you can simulate your system to fit your experimental results?
So that's actually very complicated, because since we're at least assuming the system is chaotic, it doesn't matter how precisely we made the measurement of what the initial condition is, the simulation shouldn't fit the model, because it's a chaotic trajectory. But that's at least the trajectory. But if we think about that first diagram I showed, not first, but that colorful one, we have regions where we know where the magnet ends, where the pendulum ends. And from that, if we had a very good model and a very good experimental setup, we could predict where it's going to end suitably.
Okay. I think we have no other questions then. So at this point, I would like to the jury members to start computing their grades, please. And I'll also say that we're not going to have any time until for the, any break before the last round because of time constraints. We're a little short on time. So yeah, we're going to start right away with the last round. Okay. As soon as I have all grades, I'm gonna ask them for the next team to start preparing their slides. All right, so I'd like to ask for the presenting team to already start preparing their slides. So you have 5 minutes to prepare. Okay, and please, if you're already ready and want to start, just let me know because it'll be better. And who's gonna be the presenting one again from USP?
I will be presenting.
Okay, Matheus will be presenting. Okay, so please, Henrique, give Matheus Teixeira from USP the permission to share. Oh yeah, actually, I misspoke. It's actually 3 minutes for preparation, not 5. So sorry, but Matheus, you can also already pull up your slides and yeah. Oh, nice. Oh yeah, we're seeing another screen. We're not seeing your slides. And I must say that when you're live, when you're like in person, it's really hard these things because you have to plug into the projector. So it's really an amazing time. I mean, it's kind of desperate, but it's crazy.
Just a minute, man.
Okay, no problem.
Are you guys seeing my slides?
Not yet. It's still charging. Like not charging. Sorry, it's loading. Charging. Jesus Christ. It's loading. Yeah, we can see just your screen, but not your slides. But I do like your background image. Oh, yeah, Spider-Man Multiverse, like amazing.
Great movie.
So yeah, now we can see your slides. If you can please just take out this the Zoom, diminish the size of your Zoom thing of your Zoom.
I'm trying to do that. Just
okay. Just so it doesn't get in the way of your presentation.
I can't seem to do this.
There's a minus sign there that it doesn't go away, but it's better.
Yeah, you can click on the minus sign so it becomes like really small.
Sorry. Here, find it. Okay.
Ah, nice. Okay, yeah, here we go. Okay, you have 12 minutes starting now. Yeah.
Okay, so I'm Mateus Teixeira, and I will be presenting the smashing spheres problem, number 11. So the statement of the problem is smashing two steel spheres together with a paper in between at the point of collision produces enough heat that it burns off the paper. Conducting the same experiment with the aluminum foil, you will observe concentric rings on the foil after the collision. To study this phenomenon, can it be observed for other materials? So first of all, they ask us to study this phenomenon, and we will approach that as trying to understand better the physics responsible for the observations. And also, we will try to respond if we can observe these phenomena for other materials. Okay, so first of all, the physical mechanism. So our hypothesis that we'll be trying to corroborate with statistical data. First of all, the problem states outright that the paper is burning. So there's no question about that. So we are trying to understand why the paper is burning. Our hypothesis is that the burning of the paper is a combination of its high heat capacity, about 1400 joules per kilogram degrees Celsius, its low heat conductivity, and its high and the high temperature of the collision. So basically, what we are trying to assume as a hypothesis is that because of the low heat conductivity and the high heat capacity, when the spheres collide, it's a inelastic collision, which means that for all sorts of manners, the spheres will lose mechanical energy from the beginning of the collision. And that can be in multiple ways: sound, deformation, and the most important for our hypothesis, heat transfer. So what we're trying to establish is that because of this heat transfer, the high heat capacity and the low heat conductivity, basically the temperature will change to a very high temperature, well, more than 233 degrees Celsius, so that basically the paper burns. And the low heat the conductivity means that the temperature will take more time to dissipate. That's also why we think that more heat and the impact, the more heat generated in the impact, the higher the temperature will be, and the longer it will take to dissipate, which means that it probably will have a higher, a greater hole made by the burning. So that's what we are trying to achieve with our data, and that to try to corroborate this hypothesis. For the hypothesis of the aluminum plastic deformation, we are thinking about a combination of a lower heat capacity, not exactly low, about 910 joules per kilogram degrees Celsius, a high melting temperature and ignition temperature, about 660 degrees Celsius, and the change of pressure. So basically what we're trying to establish is that because of the lower heat capacity and also the higher heat conductivity, it doesn't get hot enough to burn or melt. It also dissipates the heat from the collision very quickly, but the transfer of momentum caused by the collision will in a small area, as we will see, we will make a high pressure point that will generate the concentric rings on the aluminum paper, the plastic deformation. It will never come back as it was before. So first of all, our experimental apparatus, we got a structure with two stems, so we could control the height of two balls of chrome steel with diameter 50.8 millimeters and mass of 0.5354 kilograms, both. And with this apparatus, we could change the angles and the heights of the two spheres. So we could change the total mechanical energy, total potential energy that would become kinetic energy in the moment of collision. Okay, and total mechanical energy. We are also utilizing another support for taping the paper with enough area to the collision, so the collision can happen, both with the paper and the aluminum foil. But I would also like to say that we could have we weren't able to do this with multiple different sizes of steel spheres because they are quite expensive. But we could say that with our hypothesis, the diameter would be very important, because if a lower diameter and the same density, the mass would be lower, so the total energy, and by that aspect, the total heat transfer would be lower, and probably wouldn't, in a certain limit, wouldn't burn anymore the paper, or and the higher area of the sphere, a higher a bigger sphere will probably make a higher area, which will make the heat flux smaller, and it will have less pressure as the area of contact will be higher. So that it is important, the size of the spheres and the masses. Okay, so the experimental data for the paper. We did multiple collisions, and then with what we found in our literature, we estimated the total heat that is being transferred to the paper. Basically, we calculated the total mechanical energy by finding out with the software tracker the heights of the spheres, utilizing as a base the size of the apparatus we are using to hold the spheres. So we found out the total height when they were left to collide, and then we had the total energy. And the literature suggests that about 5% of the total energy would be transferred to heat. So with that, we can figure out the total heat that would be transferred to the paper. And then what we're trying to establish is that with higher heats, with a higher heat flow, the bigger the radius will be of the size of the hole. Establish that the hole is approximately a circle. And as we can see, even though we had some technical issues and didn't have a lot of data, we can see that they do follow a pattern of as the higher the heat energy, the higher the radius is, which corroborates with our hypothesis of why the burning process is happening. Okay, so about the concentric rings in aluminum foil, the literature also suggests another possibilities aside from our hypothesis. One of them is a shock wave. It maybe can be a shock wave, but the literature has surpassed that by doing the same patterns as we have obtained in the aluminum foil with the collisions of the spheres, by doing the hydraulic press experiment, where they augment the pressure slowly with a shear in contact with the aluminum foil in a solid surface, and it also generated similar concentric rings. It could also be because of the melting point, so the foil could be melting and then forming this deformation. But it's not the case, as we have said before. The melting temperature of aluminum foil is quite high, and the mixture of the high heat conductivity and the lower heat capacity makes it so that even with significant energy, initial energy, the total heat wouldn't be enough to change the temperature to enough to a high enough status so that it would melt. So we focus now on our hypothesis. Again, we are utilizing the total energy by calculating the heights with the tracker and calculating the total energy with the initial potential energy of both spheres. And here we're trying to determine if the pressure and is important. So what we have done here is a graph of the total mechanical energy over the radius of the outermost circle. Why is that? Well, the total mechanical energy calculated as we have is the total potential energy in the beginning. And the total potential energy will become the total kinetic energy of both spheres, which is directly correlated with the velocity that the spheres will have in the moment of impact. So the higher the mechanical energy, the higher the velocity of impact will be, and that means the higher the moment of the linear moment of the spheres will be when the impact happens. That means that a higher transition of moment will happen in a small area, which means it will probably have a higher pressure. So again, we have obtained some results with the mechanical energy and the radius, and we have seen that they do also follow a pattern, even if it's not completely linear, of having higher radius or with when you have higher mechanical energies as an initial condition. Also, another factor that corroborates our hypothesis for why the aluminum foil is basically doing this plastic deformation is that when we increase the moment by increasing the velocity of impact of both spheres, the quantity of rings will increase too. That is established in literature, and we also have made an experiment that proves that. Okay.
Okay.
So
I think we're done with time. Okay. So the opposing team can ask questions.
Okay, so I wanted to ask about, can you go to slide number 3? I'm sorry, slide number 4. So, no, the previous one. I wanted to ask you, what's the uncertainty on the mass? Do you have 4 significant figures for the mass?
I calculated the mass with the diameter and with the density from steel, and I obtained this measurement.
Can you go to the next slide? I have a. You said that the diameter of the ball influences the size of the size of the hole. I don't remember correctly. But
what I was trying to say. Oh, sorry. You can talk.
No. You can say.
What I was trying to say is that the size of the sphere will influence if the burning process will happen, because if the sphere is too big, the flux, the area of impact will be higher will be greater, and the heat flux will be lower, so maybe it won't have enough change in temperature to burn out. And also, as the higher area is established, the pressure will also possibly be lowered enough so that the concentric rings are lesser or not made at all.
Okay.
Also,
sorry, I'm sorry to interrupt you. I just want to make a follow-up question that may be a little naive, but isn't theoretically only one point
But
of
you have to
contact
make this
between
question after, because now we're out of time, unfortunately. So
Okay,
the opponent team uh, has 3 minutes to prepare their presentation, starting now.
Can I stop sharing my presentation?
Yeah, sure. And also, if you please could have the name of the opposer, because then we'll already allow you to share. I mean, the opponent. Sorry, not the opposer. Yeah, who's gonna be the opponent?
It's going to be Leonardo.
Leonardo.
Yeah.
Ah, Leonardo. Okay. So please, Henrique, allow Leonardo to share the. You have 1 minute. Ten seconds. You can already try to start screen sharing, just for us to see.
Can we ask for a tactical timeout?
Yeah, for sure. So you get 1 extra minute.
Okay, thank you.
I think yeah. I think you still have. Well, this was the last one, I think.
Could we get another technical timeout, please?
Okay, I think
it's our last one.
But let's see. Oh, it is okay. You had 2 still, right? You were aware of it. So okay, you have one more then. Because I lost count, honestly. I don't know if you had one more or not. I was just checking that out here. But yeah, you were right. You have 10 seconds.
Okay, I'm ready for the opposition.
Okay, yeah, so you can go ahead. You have 5 minutes.
Just 1 second.
Oh, wait, okay. Okay, you have 5 minutes then, starting out. Go ahead.
So I'm Leonardo. I'll be the oppositor of the problem smashing spheres presented by Mateus from USP. So the problem states that smashing two steel spheres together with a paper in between at the point of collision produces enough heat that it burns off the paper. Conducting the same experiment with aluminum foil, you will observe concentric rings on the foil after collisions. Study this phenomenon. Can it be observed for other materials? So first, I would like to start with the positive aspects of the presentation. So the first one is that they proposed an underlying physical mechanism. They explained all the physical phenomena involved in the experiment. They used a literature to approximate values that were difficult to measure the energy transferation. And the theoretical approach was really good with the correlation of the energy. We have some nice experimental pictures. And the approach with tracker was a good way to analyze the data. It's a really good software that helps in this experiment. So about the lacking aspects, I think the first one, and for me the major problem would be that the low variation of experimental parameters. They didn't vary the height. They didn't vary the material of the ball. They didn't vary the material of the. For example, they didn't use, for example, a polymer instead of aluminum to see the results. And also, they didn't vary the size of the string, for example. And another thing is that the low control in initial height, because as we could see from the experimental pictures, the person would need to hang the balls in the air and it would release to generate the collision. So it's not controlled, the initial height, because it depends on the human eye. And the uncertainties determination were not so clear, especially in the graphs and the mass and the diameter of the ball, the uncertainties related to those phenomena. And in one slide, you have mentioned the melting temperature, and I didn't understand the importance of the melting temperature for the concentric rings. And another thing is that on the plots of the graphs and tracker, you have many outliers, points that were out of far from the curve, the straight line, sorry. And you didn't answer the question of other materials. You can see that if the problem states that can it be observed for other materials, you didn't answer this question. And hold on, let me pass to another. And I would propose 3 interesting topics for discussion. The first one would be, can concentric rings be observed for other material foils? The second one, can the vibration of the spheres generate more collisions? For example, because we can see clearly that it has only one collision, but maybe we could see some smaller ones that are not so apparent for us. And the third one is how the ball material would influence the problem. Can I stop screen sharing? Can you hear me?
Yes.
Can I stop screen sharing?
Actually, if I could just ask you to continue sharing just for a moment so I can discuss some of the topics in the discussion.
Yeah, sure.
Okay, so can you go back to the problems that you found on my presentation? Just for a moment.
1 second.
So just to determine some things, it's true we had a low variation of experiment parameters because we lost a lot of data because of how we filmed the experiment. That's completely true. We probably should have done with more than one camera, and we couldn't do that. I didn't thought of doing that in the moment. The low control in initial height, even though we are doing it for in the human eye, it's not that difficult to determine a different enough height, so the difference of mechanical energy in the system is greater enough, especially if you're measuring lifting one ball and lifting two balls. So it's not really that much of a problem. Uncertainties determination. So just to finish, actually the diameter is established by the factor that we bought the steel balls, and the mass I really didn't it's a specified uncertainties, and for that I'm sorry, but the uncertainties and the graphs were actually a mixture of uncertainty propagation of calculation with the energy equation, and we also basically utilized how we measure the height as a uncertainty for the measurement of the height and the radius, basically. So now we can talk about the interesting topics you mentioned, and the next slide, if you.
Okay, go ahead.
No, please. You have a question?
First, I would like to question about the second topic, the low control on initial height. You say that it's not that difficult for the human eye, right? But each time you do this experiment, you have an uncertainty position of your vision. So each time you have an error associated that was not considered. So that's why I put it the low control. The
Actually,
low control initial height as a Laskin aspect.
Actually, we didn't try to get a specific height at each time. We just tried to vary enough the height so the variation of the energy would be significant. So the uncertainty wouldn't be exactly important in this case. But I understand your topic. Do you have more questions, or can we talk about the interesting?
Yeah, I would like to ask. What are those outliers in the plot? If you can like screen share for me, would you? For a second.
Yes. If my computer allows me.
Yeah, sure.
I will try to do that. Can you guys see my presentation?
Yeah, I would like. If you could go back on the tracker. For example, you have like many outliers on the plot, right? So why is those points appears?
Oh, that's probably again as you can see, the uncertainty of the measurements are quite high. That is actually because of the way we measured the radius. So it probably isn't the more precise way, and that's probably why you had so much outliers, especially in the rings, because it's can be tricky to determine what's the outmost ring or concentric ring on the aluminum foil. But I believe that the pattern we don't have a lot of experimental data, but we can see enough of a pattern to understand that they do agree with our hypothesis.
Thank you. Can I just do one more question, and then we can go to interesting topics? Could you go back for the slide you say about the temperature, the melting temperature, the melting temperature?
Oh yes, of course. I think it's the slide.
Yeah, I didn't understand how it matters for the theoretical development of the problem, the melting temperature.
Well,
I mean, in terms of the concentric
later, because now we're off time. Now, the reviewer has 2 minutes to ask questions for both the opponent and the presenter team. Starting.
Hi everyone, can you hear me? Is everything okay?
Yeah.
So for the presenter, the holes that you see in the paper are results only on the burning process, or there are other things that determine the holes that we see on the paper?
What do you mean? Sorry, I didn't quite understand the question.
The holes on the paper are just by burning, or there are another things influencing this?
Well, because of the high change of temperature, the holes of our hypothesis is that the holes of the paper is probably mostly because of burning. There is a possibility that with a high and a low enough
I'm sorry to
height or
interrupt. I'm
Of
on
course.
time. I have another question. Is the ductility of the material and the fracture toughness important in these experiments?
Sorry, can you say that again?
The ductility of the materials and the fracture toughness for both teams. Just a yes or no. Are they relevant?
No.
Do you agree, opponent team?
Could you do the question again? Sorry.
Yes, the ductility and the fracture toughness of the materials, the paper and the aluminum, are they important for the phenomenon?
I would say they are.
Okay, thank you. Just the last question. For the opponent team, the reporter, you nullified you falsified the hypothesis that the aluminum was melting, right?
Yes.
Okay, thank you. That's all the questions I had.
Okay. So now 3 minutes for the. No, actually, 1 minute for the reviewer team to prepare. And I think Unicamp doesn't have any other timeouts.
Hello.
Unicamp team wants to ask for a timeout, please.
I think you don't have any other timeouts remaining, right? I said like you already used the 3.
Yes. I don't remember using the 3 timeouts.
We only use 2.
Okay.
For calculations, but there's no problem. I can share my screen. I need the host to enable me.
Yeah, please, Henrique, just enable Gustavo to.
Yes. Can all of you see my screen?
Yes.
Okay.
Go ahead. You have, let's see. Again, you have 3 minutes to present.
Okay.
So go ahead.
My name is Gustavo, and I will be the reviewer for the problem 11, smashing spheres. So just to recapitulate the problem statements, smashing two balls together with a paper in between at the point of collision produce enough heat that that it burns off the paper. Conducting the same experiment with aluminum foil, you observe concentric rings on the foil after the collision. You study this phenomenon, and can it be observed for other materials? So to recapitulate the report team, they did an excellent job exploring the physical mechanisms for the heating hypothesis, explore the relationship between the movement and the resulting heat, and show images in the video that really clarify what have they done. But some negative aspects of their presentation was that how some values were obtained, such as in slide 3 and 4, how to guarantee the alignment and the speed of the spheres in the paper, some lack of variation of relative parameters. They dismissed the heat hypothesis, but did not formulate another one, and they did not explore the patterns formed on the foil. So now for the opponent team, they noticed the lack of uncertainties and many significant figures. And they also noticed the lack of control of the experiments, the outlier on the fits, the variation of the ball's the lack of variation of the ball materials and number of bounces, and highlighted the incompleteness of the assessment of the problem. However, they did not explore the ductility and the fracture toughness, could not, that they say that it was important, could have observed some confusing results on the graph beyond the bad fit. Did not ask about the ripple mechanisms and how the pattern is formed, which is the main thing that I want to touch about. So I would like to invite both teams for some discussion points. The main one that I want to discuss is in terms of a physical phenomenon. What's the physical mechanism for the ripples that we are seeing? Both teams did not mention this at all, and I would love to see some discussion on this point. And is it possible to determine more relevant parameters with more experience? What new parameter would we see? Could you imply any aspect of the movement from the motion of the ball from the pattern formed? So I invite now both teams to see the fight.
All right, you have 4 minutes.
Okay.
So first, the report team. Since you falsified the heat hypothesis, what are you saying that is happening on the ripple mechanisms? What are the ripple mechanisms?
I can explain that. We are trying to predict, well, our hypothesis is that the pressure made by the impact of the sphere with a high enough velocity is causing both the ripples and it causes the ripples, and it is backed up by literature because you can do the same patterns with a hydraulic press and a sphere ball, as we have explained before. And yeah, that's it. That's why we try to match with the mechanical energy, because with the total mechanical energy, we can determine the velocity. That was one of your questions. And with the velocity, you can determine the momentum of both balls and the difference of the momentum for the first and the pressure.
And the opponent team agrees with that explanation?
I partially agree. I do think that the pressure and the heat influence the mechanism on the ripples, but I don't think it's probably the most effective mechanism, but I don't think it's the only one.
Do you think that maybe for the both teams, bulk instabilities have an impact on this? I was expecting a strain stress graphics because, well, you can talk about it.
I don't think so. I think the metallic structure of the aluminum foil is actually quite important too. So to the specific ripple, the specific patterns that are happening because of the pressure. And if you wouldn't to go further than that, the cellulose structure in the paper, and in both the paper and parchment paper, it was part of my presentation, but I couldn't do it on time. We actually could prove that the burning happens in other other materials if they have similar initial parameters in the ways that the heat capacity and the heat conductivity is they are good enough for the temperature to reach a number higher than the burning ignition. So for a parchment paper that was 260 degrees Celsius, then we could do easily that multiple times.
Okay, do you agree, the open team?
I would say that if you have a rigid structure like a metallic apparatus supporting the aluminum foil or the paper, the instabilities would be a minor effect, so they wouldn't be so significant for the problem.
Okay, since you touched on that point, what do you think would happen if we use another metallic material, such like copper or, I don't know, titanium?
I would say that sorry, go ahead.
No, you can go.
I would say that would have a higher deformation, especially with copper. And I'm not 100% sure, but my intuition says that the number of concentric rings would be bigger.
And do you agree, the report?
Yeah, I think it actually, I would have to understand better the metallic alloy that we are using for exactly, it is pure copper, it is a alloy. And then with that information, we can try to estimate what can happen, if the patterns happen, if they are different in some way. I do believe by intuition that probably a pattern of deformation happens.
And opponent team, what would you suggest that the reporter should know to predict for the phenomenon for another metallic structure, such like copper?
Yeah, and everybody can join the discussion now too. Yeah.
Okay, so I would say that probably parameters like fusion temperature, not fusion temperature, sorry, fusion temperature, and probably the deformation pattern of the metal.
Do you think that would be sufficient, reporters?
Oh, again, we have tried to falsify the possibility of the deformation being caused by melting the metal. So it would be important to know, just because if it is low enough temperature, it could happen depending on the high conductivity. If it has low enough conductivity of heat and a high enough heat capacity, because it can change the pattern if it is actually melting, but I highly doubt it that for any matter it will happen. Actually, the thing I would say is more important is how the metal is arranged, how the alloy is arranged, the atoms and the structure.
Got it. I will call Álvaro now. I think he has something to add to our discussion. We can't hear.
We can hear you, Álvaro.
Okay, sorry. I'd like to ask for the reporter. It's a yes or no question, please. Did you measure the pattern formated and its aspects, such as the radius of the inner ring and of the outer rings? Yes or no?
As actually mentioned, we use one of this data in the presentation. The outer rings, the diameter of the outer rings were actually used.
Okay. Do you have any uncertainty on that?
Yeah.
Yes or
so.
No? Yes or no,
Yes.
please. Did you show on your presentation? Yes or no?
Yeah.
Okay.
Just to
now
make
for
it
both
clear.
teams, please. I think from problem statement that the pattern formed is really important to the solution of the problem. And I'd like to ask, what are the aspects of the ball, of the ball's movement and or other properties that can be inferred from the formed crater? For both teams, please. The opponent first.
Definitely, I would say the ball material would change. It's an important parameter, and I think it's the main parameter. But of course, the diameter of the ball, and yeah, I think that those are the most relevant parameters. But yeah, in terms of motion, I think that if you, for example, suddenly change the trajectory of the ball, the pattern would be slightly different.
Just the time is spending. Just to make a quick question for the opponent team. Are you satisfied with the solution that the reporter gave us? You think that it fully comprehend the phenomena and all its nuances?
I think they did a very interesting analysis, but it could be enhanced. It could be, the experiment could be more, how can I say that? It could be enhanced in terms of variations of parameters, especially. But I don't think they fully answered the statement, especially the last question about the other, when they ask about other materials.
All right, thank you very much. So I would like to ask for the last concluding remarks of the reporter.
Okay, so I'd like to thank both Unicampi and Federal University of IBC for the interesting remarks on my presentation, interesting remarks on my experiment, on our experiment, and how we could improve and enhance the experiment for a more precise, maybe a more concise or a more precise explanation of the phenomena that is happening. Also, I would like to thank you all for being here and watching the presentation and being interested in this problem. And I would like to thank my partners for helping me with the experimental data and with the setting up of the experiment. Thank you.
All right, now we move on to questions from the jury members. So jury members can raise their hands and ask. So yeah, Barbara was pretty quick in this one. You can ask away.
I guess I saw the same solution earlier today, but so I have two quick questions. One is for everyone because everyone was hammering on the topic of material, but I didn't get a clear answer, like a specific clear answer. So if I change the material, say I have a different metal, what changes? Very concisely. And for the reporter, what would you change in your experimental setup if you had to redo everything? Like, how would you control better your experiment so you have a more clear picture of what's going on?
I think I will answer the first question. I will let the others answer it, and then I will come back to the second question. The materials and specifically as you asked, if the metal is changed, the pattern probably is going to change. If not, the shape as concentric rings, the quantity of concentric rings, or the radius, the total radius.
Can I just specify a little bit more on this question? So say I have a more conductive metal or a metal that can deform more. It doesn't necessarily have to be a specific metal. What happens if it's conducting more and if it's deforming more? What happens to the concentric rings specifically?
We probably increase in number and in radius for the outermost, both the outermost ring and the smaller ring for the first smaller ring in the center.
The opponent.
For a conducting material, I would say that the number of rings would change, and for a what was the other one? Sorry, can you repeat?
If the material is more deformative.
Yeah, deformity. I would say that the inner radius and the outer radius would be bigger.
I believe that for a more malleable material, the inner ring will remain constant, but the outer ring will expand. And I believe that there is no dependence on any thermodynamics parameters of the metal. So I don't think that's relevant. So for a given malleability, and a change in the thermodynamics of the material, we would have the same ripples.
So for your second question, I would definitely increase the number of cameras so I could have a more complete three-dimensional view of what's happening, because a lot of data was lost because we had a three-dimensional movement that we couldn't exactly measure with the tracker with only one camera in 3 dimensions. And so we lost a lot of data because of parallaxes and stuff like that. Also try to maybe have a background for the pendulum, so we can actually measure the exact height or the exact angle or the exact height of each spheres, maybe conduct it with more people, or more specifically, if you had like an infinite amount of resources, maybe making it more methodical how they heighten the spheres by maybe having something more programmable and more specific, increasing the height of the spheres.
Cool. Then we move on to the next jury member, Matheus Farias. You can ask away.
Yeah, my question is for the reported team, because I don't know if I understood it correctly. Like, when you measure the mass of the ball, you use the density and the radius, right? So you measure the radius and the density, you just Googled, and then you calculated the mass. Am I right?
Actually, the diameter was given to us by the where we bought the spheres. So it's a known radius, and we know the what it's made of. It's from steel, so we could find easily literature for the density, so we could calculate the mass. I thought it would probably more accurate than just trying to measure it with a simple balance.
Okay, sure.
Cool. Well, I had seen a raised hand before, but I think the jury just is fine. Okay, I actually am happier now. So that, oh my God, Claudia Lenz just raised his hand. So, okay, yes, you can ask.
I am a bit tired. I was not gonna ask, but anyway, let me just ask. Since you use the tracker to measure the initial energy, and you mentioned the literature that typically you lose 5% in the collision, but you have the tracker. Did you measure the energy after the collision? Right after?
We did. So we did, but we were worried with the results because we were worried that the energy after would have, not only because of the movement of the spheres in other directions, but also because of the other ways that they could lose energy. We couldn't exactly determine how much of acoustic energy they would lose, for example.
Yeah, but how much did you get? What was the estimate?
Estimate.
On how much energy loss?
How much energy loss?
I mean, if
I remember correctly, it was about, it varied a little, but I think like 20%, maybe.
Okay. And I would definitely suggest that you try different materials and thicknesses. Aluminum foils, they exist in different thicknesses, and paper as well, and polymers and stuff like that, and Kapton and whatever. Would be nice to see. All right. Thanks.
Cool. Yay. Thank you very much. Now, the juries can compute their grades and send them through the forms. And I think that's it. Yay. Let's see. All right. So we're gonna have a 10-minute break now. So after the juries decide their marks and everything, we're gonna keep I think we're gonna stay in the same room. Henrique, is that it? Okay, so we're gonna stick in the same room. But all the jury members can give comments on anything they want within these 10 minutes. So you can just talk with each other. And yeah, we'll return soon with the results of the last physics fight. So I'd like to, thank you everyone that's watched us throughout this entire day. There's 4-hour, 46-minute discussions on physics problems. So yeah, if you want to clap or pretend you're clapping on your camera, yay! Thank you so much for everything. This was the 4th edition of the Brazilian Physicists Tournament. And well, I think Henrique will put some songs for us to hear on the broadcast, but you all can keep talking about anything you want. So within these 10 minutes. So yeah, I mean, if the jury wants to give comments on everything, like on anything, on something that the students did or something like that. Oh, no, but yeah, no, não, agora já fala em português, né? Já parou a competição. Pronto, vou falar em português. Não, mas não vão tirar, não, porque essas músicas aí são sem direitos, as que a gente achou. Não são as músicas com direitos, não. A gente pegou músicas que não tem direitos. Eu não sabia que existiam, mas o Henrique achou.
A música em que o artista não recebe dinheiro.
Exato, essa aí que a gente gosta. Né? Porque o BPT também não está recebendo dinheiro para nada. Entendeu? Então a gente é a gente é a favor disso. entendeu? Do trabalho, assim, de graça. Tô brincando, mas é isso aí, gente. Aí os jurados podem fazer comentários também, né? Tá, gente? É porque a gente tá muito atrasado aí com o tempo, e por isso que na final a gente poupou aí de comentários, mas vocês podem comentar aí, conversar com as equipes. Eu vou, enfim, passear em um pouquinho lá.
Muito bacana ver ver as montagens do pessoal, ver as medidas. Agora, me deu a sensação, em vários que eu assisti, que faltou um deltazinho a mais para fazer um trabalho completo. Aí eu não sei se foi questão de tempo, se foi questão de disponibilidade, de alguma coisa, porque, assim, vários desenvolveram, né, todo um ferramental, um sistema, fazer medidas, e deixaram de testar, né, de ir um pouco além em algumas coisas que seriam muito simples de fazer. Então, assim, fica os parabéns aí por, né, tem equipamentos aí que o pessoal montou, muito bonitos, né, com a capacidade de medida fantástica, mas eu acho que faltou aquela visão mais crítica para ir um pouquinho a mais, tá? Então, quem sabe vocês se preparam aí, a equipe vencedora, né, vai esse Epson a mais e para ter um excelente resultado aí no Mundial. Parabéns para todo mundo.
Talvez um contraponto, se alguém está fazendo se está fazendo absolutamente todos os parâmetros de um problema só, talvez não está fazendo todos os problemas que deveria, está focando demais num só.
Eu não sei, porque eu nunca organizei uma equipe, mas eu imagino que a ideia de ter uma equipe grande, né, você poder ter diferentes grupos, né, Bárbara, trabalhando em problemas específicos.
Eu nunca fiz o ITT, mas na época que eu fazia YTT, cada um trabalhava em 3 problemas e mesmo assim estava no avião terminando os negócios, porque não dá tempo.
Não dá tempo, eu imagino.
É bem isso mesmo.
Claro, tem tantas outras coisas na vida para fazer também, né?
Posso fazer um comentário de exemplo desse experimento que eu acabei de fazer? Esse experimento, que nem a pergunta da Bárbara sobre se a gente pudesse refazer o experimento, ela é relevante porque a gente acabou fazendo o experimento de uma forma muito corrida e medindo os dados de forma muito corrida, e a gente perdeu dado por conta da filmagem de erro bobo, de colocar mais de um celular é uma coisa que devia ser pensado quase imediatamente em outros experimentos, tipo o Sparkler da Unicamp, eles colocaram celulares em mais de câmeras, né, em mais de um ponto. E a gente acabou fazendo um pouco corrido e acabou tirando a qualidade que esse experimento podia ter, eu acho.
Eu acho que a minha sugestão, quando eu perguntei, não era nem a câmera, era só o setup mesmo do experimento, poderia ter ficado um pouquinho melhor. Mas eu entendo, eu já fiz um experimento semelhante quando eu estava no primeiro ano, estava no ensino médio, que era 2010, teve um problema semelhante no YTT, eu estava destruindo a cozinha da minha casa, então eu entendo.
O detalhe, sabe o que eu acho? Só uma coisinha para falar no caso desse do Matheus, como ele apresentou de manhã, e aí não dá tempo de corrigir à tarde, né? Eu falei, nossa, ele vai apresentar novamente exatamente a mesma coisa e não dá tempo de corrigir muito, né? Às vezes esses detalhes acabam prejudicando, mas agora à tarde você foi muito melhor do que pela manhã, por exemplo, na sua apresentação. Então, elevou bastante, então as ideias, as discussões que você conseguiu fazer agora já melhorou bastante, né? E como tem agora uma parte de review, ainda melhora mais ainda o nível da discussão, né? Você conseguiu elevar bastante o nível, né? Mas felizmente prejudica porque como já está pronto, não há tempo de fazer certas modificações para poder apresentar. Agora, na argumentação melhora, né? Por exemplo, as argumentações, olha, não fez isso, mas pode acontecer isso, então isso já ajudou bastante na apresentação da agora.
Quando a gente... Pode falar, Matheus.
Uma coisa interessante dessa Olimpíada é porque ela não é só teórica, mas também experimental, né? E tem esse viés muito experimental, na real. Você vê, sei lá, modelos muito complexos aqui para um problema, e quando chega no experimento, você fica, pô, velho, seria legal se tivesse um aparato experimental mais bacana aqui para contemplar o problema como um todo, sabe? Então eu acho que essa parte experimental às vezes peca um pouco, mas eu também sei que é a parte mais difícil, assim, e por conta do tempo e tal, e da quantidade de problemas, talvez seja um grande desafio, né?
Eu queria fazer só um comentário. Desculpa, pode falar.
Não, fala, por favor, já falei bastante.
Queria fazer um comentário que o comentário do professor Cláudio Lenz foi, não sei se é síndrome de perseguição, mas foi uma coisa que tocou assim bem fundo no meu coração. Essa questão do aparato experimental assim, bem elaborado, né? Porque realmente foi 90% do tempo que a gente gastou no programa foi nisso. Eu devo ter clocked in, tá, umas 400 horas no laboratório só para fazer essa porcaria de experimento. E no final foi a parte de coletar dado, né? Foi dia 14 de dezembro, eu lembro disso perfeitamente. Que foi o primeiro dia que eu consegui coletar um dado. Foi o primeiro dado que eu consegui coletar. Isso a gente começando o programa em setembro. Então, foi bem corrido isso e realmente foi imaturidade mesmo, eu acho, da minha parte, de não conseguir planejar que tipo de dado que eu precisava, o que eu precisava responder. Eu fui fazendo o experimento enquanto eu ia, assim, mas esse experimento também eu tenho a intenção de fazer ele ser uma coisa mais a longo prazo, fazer outros resultados com ele, né? Então, para mim foi interessante focar tanto tempo no setup, porque eu consegui apresentar um negócio um pouco gambiarra, né, no IPT, mas possivelmente eu faço um trabalho legal no futuro. Eu queria agradecer a todo mundo também pelos feedbacks, pelos pontos a serem questionados, que tudo isso com certeza vai ser levado bastante em consideração para progredir o problema.
Acho muito interessante esse formato da IPT de discussão do problema, porque eu acho que adiciona muito. Se você fosse só uma apresentação, tipo um congresso, você tem 10 experimentos, os grupos escolhem N número de experimentos para fazer, apresentam e os jurados dão uma nota. A gente com certeza ia aprender bastante só pela a experiência de formar um experimento, mas a experiência de debater e ter mais especificidade no que a gente pode melhorar, em coisas que a gente não conseguiu compreender na apresentação, ou no próprio relapso da montagem do experimento, a gente acaba aprendendo grau de magnitude mais, assim, eu acho. Eu acho isso, inclusive...
Matheus, só uma coisinha aí, só um comentário, eu concordo. O Cláudio tem razão com a questão do aparato experimental, mas eu acho que você aprende física, vocês que estão na graduação, se você vai aprender física, você construir o experimento, é a melhor forma de você entender. Quanto mais você aperfeiçoa seu experimento, ou seja, você construir da mão, eu achei incrível. Eu, por exemplo, não tive essa experiência e fico falando, nossa, se eu tivesse tido essa experiência, muitas das dificuldades teóricas que eu tive ao longo do caminho poderiam ter sido melhor corrigidas se eu tivesse tido essa ideia de elaborar um experimento e fazer o experimento. Por exemplo, diferente de você estar no laboratório, que você tem lá nas físicas básicas, os experimentos montados, você só vai tirar medida. O fato de você construir o experimento, você precisa ir além da ideia de fazer medida. Você aprende física na hora que você olha, que tipo de medida eu vou fazer? Essa dificuldade faz parte. E para a formação desse futuro grupo de físicos, eu acho muito mais bacana. Porque quando você for fazer um experimento mais sofisticado no laboratório, ou mesmo se você for físico teórico, né? As ideias de experimento que vocês podem dar para a construção disso, para a construção daquele experimento, aquela medida pode ficar melhor se você fizer tal e tal coisa, tais e tais modificações. Você só vai ser capaz de fazer isso porque vocês pegaram uma coisa do mais simples. Então eu sempre digo, a beleza, quando eu falo para os meninos, quando a gente está fazendo, eu trabalhei muito com o experimento de robótica com os meninos, inclusive do BICT. A beleza está em saber fazer o experimento, né? Porque depois, quando você constrói aquilo ali, você tem um domínio completo da física, né, daquele experimento. Isso colabora bastante. Então, o mais simples que você fez, Matheus, e o mais sofisticado dos demais, foi muito bom. E um outro detalhe também, o tratamento de dados, apesar de, por exemplo, às vezes um não colocava uma margem muito boa, ou o erro não era bem especificado, mas vocês tiveram cuidado no tratamento de dados. Isso faz parte, ou seja, daquele experimento simples, vocês conseguiram fazer um bom tratamento de dados de um modo geral, né? Então isso colabora bastante. Então esse é o caminho. Construir experimentos isso ajuda bastante no entender física, né? Eu acredito muito nisso. Você sabe fazer física pela construção do material, isso ajuda bastante na formação de vocês. Então esse grupo aqui está de parabéns. Eu acredito que ainda vou ver muito vocês em breve em vários congressos apresentando trabalhos muito mais sofisticados por conta desse envolvimento em fazer, né? Isso modifica bastante do que você vê somente um experimento pronto no laboratório, que a maior parte de nós hoje em dia diz assim, você vai fazer uma medida, você contrata um horário no lugar, você vai lá e faz a medida, ninguém tem essa ideia de não estar fazendo mais o experimento em si. Isso ajuda bastante no meu modo de entender isso, né?
fazer um comentário? Bom, primeiramente eu gostaria de agradecer a todo mundo que participou. Fico feliz que esse ano a gente tenha mais uma universidade, né, que chegou aí. Queria parabenizar o pessoal da FMG, mandaram super bem aí, primeira vez deles. E também reforçar que, tipo, vocês falaram que acho que uma das coisas mais legais do IPT é que além de você ter todo o contato com o experimento, aprender física, você pode pegar dicas que vão te fazer melhorar em trabalhos futuros, sabe? Eu acho que isso é muito bom. E eu acho que é um evento muito importante para não só representar o Brasil lá fora, né, escolher o melhor candidato para representar o Brasil internacionalmente, mas avançar a física brasileira também, né? Avançar em termos de literatura e experimentalmente. E é isso, é esse meu comentário.
Eu concordo 100% com o que você falou. Eu acho que ter pessoas no doutorado, no pós-doc, professores, comentando o que a gente está fazendo e coisas que para eles podem parecer triviais, mas que para a gente acaba não pensando, ou a gente acaba ignorando por falta de conhecimento, a gente acaba aprendendo muito também. E foi uma das coisas que eu quis dizer com a possibilidade de debate e ter mais noção do júri. Então, por exemplo, o Edward falou que a minha apresentação melhorou. Eu primeiro agradeço, mas eu acho que ela melhorou muito por conta do júri mesmo, dando dicas e mesmo que a gente não pudesse refazer o experimento, a gente tinha uma noção, as dicas que o júri deu uma noção muito grande do que a gente podia melhorar, o que a gente podia tentar analisar melhor, o que a gente podia tentar entender melhor fisicamente.
Gente, eu queria só fazer um comentário aqui. Eu estou vendo uma discussão aqui no chat. Eu queria convidar a Pietra e a Bianca para elas se manifestarem, conversarem sobre essa questão de mulheres na ciência. Por favor, manifestem aí.
Eu tô aqui no chat do júri falando, aumenta essa diversidade aí do próximo ano, pelo amor de Deus.
Gente, pior que eu acho que nem ia participar, foi, tipo, por muito incentivo do pessoal, assim, da gente, tipo, conseguir... Real, tipo, nem em relação a ganhar o e bem sobre, mas, tipo, assim, ter realmente representatividade acerca, tipo, disso mesmo, de mulheres dentro do time e, tipo, participando de um mundo, querendo ou não, majoritariamente masculino desde muito tempo. E nisso foi um prazer muito grande estar aqui participando com vocês. Eu espero que a equipe, tipo, que vá para o internacional, tipo, seja, tipo, muito bem sucedida. E assim, ano que vem, com certeza, vão estar aí de volta. E espero que com mais garotas também, que até na nossa disciplina, que tem muita pouca até menina, só que também tem mais gente.
E Bianca, você quer falar alguma coisa? Abre o microfone aí, por favor.
Eu só quero agradecer. Eu não sei se vocês perceberam, eu não sei se dá pra ver. Eu tô com a blusa de Faça Ciência como uma garota. E é isso, gente. Gostei muito dessa competição. Achei muito produtivo. Esse final de semana foi incrível.
Só um comentário sobre essa questão de mulheres na ciência. Aqui na UFOB a gente fez um trabalho no ano passado, 2019, o último ano que a gente teve uma vida normal, né, que foi um projeto Meninas da Ciência, que era encabeçado pela professora Cristine da Química, né. A gente tinha um trabalho que era falar um pouco sobre robótica educacional no ensino médio para as meninas, né, então o curso era só com as meninas, então a gente preparou o roteiro, quem dava era uma menina da engenharia civil, inclusive, né, ela está para formar agora, e ela deu o curso para o pessoal, fez a construção da apostila e aí ela ia para as escolas, a gente formou um grupo de algumas garotas e ensinava robótica para elas, né? Ela trabalhava lá e falava sobre Arduino e tudo mais. E o legal é que uma dessas meninas hoje veio fazer física, está fazendo física com a gente aqui em Barreiras, ela é de uma escola estadual, e ela olhou nossas apresentações, fez parte dos grupos, falou, professor, a gente gostou muito do que vocês fizeram e a gente começou a atrair a mulherada. Então, na verdade, para atrair as meninas, a gente precisa começar a fazer um trabalho de base, né, na educação básica, né? Então, vocês que são as futuras físicas, né, a Bárbara, que está já fora há muito tempo, que é uma pessoa que é engajada nessas coisas, então, é um trabalho que a gente precisa fazer em conjunto, em termos assim, ó, ação. Vamos às escolas, vamos começar a fazer divulgação científica, vamos atrair a mulherada para fazer física é para todo mundo, né? Porque ainda é um ambiente ainda muito formado por homens, brancos, na sua maioria. Então a gente tem que começar a fazer com que essa diversidade apareça assim, ó. Vamos lá na escola, vocês apresentando as atividades. A estratégia foi justamente essa. A ideia era que vocês apresentem, que vocês façam essas coisas e vocês criem esse ambiente para atrair esse pessoal para a universidade, para fazer esses cursos de base. Então tem agora meninas na engenharia civil, tem na engenharia sanitária ambiental e tem na física e na química. Então a gente começou a atrair muita gente para fazer ciência dessa maneira. Então é uma forma de vocês fazerem engajamento, não só fazer já a física só mais de base, mas também fazer essa questão de divulgação mais ampla para atrair a mulherada. Isso ajuda bastante fazer esse tipo de coisa, né? Então, ter um engajamento é muito bom, né?
Não, concordo completamente. E, tipo, na realidade, é que essa questão de ser mulher, tipo, no meio da ciência, assim, é uma coisa que, querendo ou não, intimida muito, tipo, no começo. Eu, na minha pré-adolescência, já cheguei a me perguntar, assim, até que ponto, sabe, certas coisas não seriam mais fáceis nesse sentido, tipo, em relação ao intelecto mesmo, tipo, sobre ser mulher ou não, entendeu? Mas, e dependendo, se você der sorte na vida, você vai conseguir, tipo, encontrar pessoas muito boas que vão te dar apoio durante todo o processo. Mas, se não, também existem certas, tipo, pessoas que intimidam muito já, tipo, te menosprezando a partir daí, sabe? Então, eu acredito que seja muito importante por essa questão realmente da criação de base mesmo, porque a gente falar disso é muito diferente do que você sentir isso durante seu crescimento, sabe? É uma coisa muito, muito real, basicamente.
Formal aí, galera. Não tava querendo colocar as meninas on blast. Era mais pro resto do pessoal se tocar que, tipo, vamos ampliar os horizontes um pouquinho ano que vem.
Só falando, nas últimas 2 equipes brasileiras que foram da Unicamp, tinham pelo menos 2 mulheres na equipe. Então é isso aí. Esse ano a gente teve bem menos, acho que só a UFMG tinha mulheres, mas vamos voltar aí a dominar as equipes.
Posso dar um palpite sobre esse assunto?
Pode.
E fazer um convite aí para as meninas? Boa tarde, eu não participei aqui hoje, mas ontem foi bem legal. Pena que estou com a vida bem cheia. Meu nome é Débora Menezes, eu sou a atual presidente da Sociedade Brasileira de Física e sou professora aqui da Universidade Federal de Santa Catarina. E eu coordeno um canal no YouTube que se chama Mulheres na Ciência, e ele tem um parceiro no TikTok voltado para adolescentes que tem muitas seguidoras, né? O último vídeo que uma aluna minha fez teve 90 mil visualizações em algumas horas. Então eu deixo aqui o convite para as meninas me procurarem e fazerem um vídeo tanto no canal quanto no TikTok falando do Brazilian Physics Tournament ou International Physics Tournament, para convidar outras meninas que têm uma penetração bem grande entre as meninas de ciências e acho que por minha causa também na área da física. É bem fácil me achar, é só mandar um e-mail que aí eu passo as instruções para vocês. Também é super fácil, porque eu tenho uma equipe bem azeitada, desculpa. Só tem que fazer um textinho curto e ir para a telinha, gravar alguma coisa no celular. Fica o convite aí. Quem sabe, nas próximas edições, eu vejo aqui mais caras de meninas.
Gente, queria fazer só um comentário, que vocês sempre vão ver meninas na equipe da UFMG. Isso foi uma coisa que todo mundo, que a gente decidiu, e a gente decidiu que era obrigatório ter a presença de meninas na UFMG. A gente queria, pelo menos para essa primeira, dividir metade, mas não deu. Mas a ideia é daqui a pouco ter uma equipe completa de meninas da UFMG.
Eu queria fazer um comentário também, que imagino que deve ser um problema semelhante com o pessoal da USP. É claro que não é coincidência que o time só tem homem, né? Tem todo problemas sociais, estruturais, de todo o machismo que a gente tem na ciência e tudo mais. Então não é coincidência que não foi aleatório. mas a gente está com, eu imagino que a USP também, mas não posso falar pela USP, né? A gente está com bastante dificuldade para achar pessoas para integrar o time. Então, esse ano foi meio que assim, quem estava disponível, sabe? Quem conseguia ir no laboratório, porque todo mundo morando longe, pandemia e tudo mais. Então, a gente teve a batalha de conseguir recrutar qualquer pessoa. Então, o ideal, o certo, o que a gente vai focar em fazer nos próximos anos, claro, é ter maior diversidade na equipe. Mas primeiro a gente precisa de uma equipe.
Isso aí é um problema aí que acontece sempre, né? Você tentar arranjar pessoas para participarem, né, do torneio. Mas eu fico feliz, assim, que tá crescendo a participação, pelo menos em diferentes localidades, né? Então, isso é muito interessante também. Então, se vocês conhecerem até pessoas de outras universidades e tal, isso é muito legal, entendeu? Que o torneio em si crescesse mais e mais. Poxa, mas a gente tá muito feliz de, na quarta edição, ter 4 equipes, né, de 4 diferentes universidades, e a gente entende também que é difícil, né, a pessoa conciliar, vou conciliar a minha graduação com essa competição, né, porque isso demanda muito tempo, demanda muito esforço e tal, mas é muito interessante ver que, poxa, todos vocês aqui que estão aqui
mecânica clássica
fizeram isso, exatamente, né? Eu não vou nem falar sobre a minha situação, mas enfim, tenho histórias ótimas, inclusive, para contar de, assim, chegar tava fazendo, sei lá, 7 matérias na UFABC, aí, sei lá, fiz as provas e tinha competição do PT, aí, enfim, fui virtualmente reprovado em, sei lá, 4 coisas e representar o Brasil é um negócio difícil, foi Jesus Cristo, né, que vergonha. Mas aí, enfim, na volta, na P2, eu recuperei de uma maneira maravilhosa, assim, é um negócio que eu nunca fiz na minha vida. Enfim, nunca mais fiz, né. Mas foi doido. Enfim, mas eu fico muito feliz que todos vocês aceitaram esse desafio, entendeu? Que estão aí animados, que vocês estão aí resolvendo os problemas, porque é um sonho, assim, pra gente ver tanta gente participando, né? E lembrando que, o IPT aqui no Brasil é muito jovem ainda, né? Tem 4 ou 5 aninhos só, né? A gente começou lá em 2016, formando a primeira equipe, agora chegamos aí em 2022. Em breve a gente vai ter a formação aí né? Vai saber quem vai para o internacional, mas ano que vem a gente já tem que se preparar para organizar tudo. Mas eu fico muito feliz, assim, com muitas pessoas participando. Quem sabe, né? Ano que vem presencialmente, vamos ver.
Queria lembrar e parabenizar que nos fights da manhã, hoje, a gente tinha 2 chairs aqui no IPT,
verdade.
Maria e a Mariana. Parabéns, gente. Tipo,
por sinal, duas ex-participantes também.
Parabéns, pessoal.
Verdade. O nosso relógio da final também era feminino. Era uma relógia. Maria... Tô brincando. Mas é verdade. Teve bastante gente participando, assim. Eu até tentei chamar... porque agora voltando para o outro tema, né? Tentei chamar várias ex-participantes assim, que eu conhecia também do YPT, por exemplo, a Amanda também, que a Bárbara deve conhecer, enfim, mas aí a gente tinha vários compromissos aí, acabamos, enfim, ficamos até uma procura bem doida, assim, para conseguir os jurados, né? Mas ano que vem, tomara que a gente consiga formar esse corpo de jurados com antecedência maior, para a gente poder, enfim, não ter, por exemplo, até o mesmo team leaders julgando as outras equipes, né, e, enfim, ter realmente pessoas externas julgando o trabalho de todo mundo, porque isso seria o ideal mesmo, sabe, isso que a gente queria, mas esse ano não deu para fazer, mas a gente está tentando, enfim. Esse ano aí conseguimos pessoas internacionais, né, mesmo, conseguimos aí o Matheus lá de Harvard, a Bárbara também, então, assim, isso é legal, que a gente vai crescendo aí conforme o tempo passa. Aí, a gente está terminando aqui a apresentação aqui, e aí daqui a pouco assim, você já me mandou até, eu tô convertendo para PowerPoint para ficar bonito, é isso que eu tô fazendo agora, hein? Eu não sei nem quem ganhou ainda. Você tem PowerPoint, que eu me poupo o trabalho de converter, então é só me mandar. Ai, que alegria, não é mesmo? Eu sinto saudade de participar, assim, como participante, né? Enfim.
Se quiser integrar, tinha o FABC.
Ah,
Tá no
não,
mestrado
pô,
ainda, né, Matheus?
que mestrado não, comecei doutorado já. Integrar não posso
Já?
integrar nada. Mas pode me chamar pra ser líder, ó.
Ah, é?
Inclusive, até aqui na
Tá
minha
querendo
guild.
roubar o papel dos líderes.
Ó.
Roubar nada.
Não, mas eu tô até tentando formar
Não,
um time aqui na minha faculdade, mas enfim,
Cadê
mas
o
o
time do
pessoal
Canadá?
isso. Não, então, tem, tá? A gente. Quer dizer, a gente, né? Enfim. As poucas pessoas interessadas em realmente, né, fazer o bagulho estão trabalhando, né? Mas sei lá, eu não. Vamos ver o que acontece, né? Eu queria que eles fossem mais animados, né? Mas.
Eu fico impressionado que não tem mais time internacionalmente. Pra mim, a primeira vez que eu vi do IPT, eu fiquei pensando, meu Deus, como é que esse evento é tão underrated assim? Mas tá crescendo, né? Bastante.
Então, outras coisas que eu ia falar, então. É legal de ver que tá crescendo, eu esqueci de falar esse ponto, mas assim, tá virando disciplina em várias universidades. Isso é um ganho, assim, muito legal pro IPT, entendeu? Por exemplo, na Unicamp eu sei que é uma aula, que na UFBC virou uma aula, na USP eles não têm aula, mas eu acho que tá tentando virar. Na Unicamp já é também uma aula do mestrado e do doutorado, eu acredito. Na UFMG também, eu acho que estava faltando isso, falar da UFMG. Enfim, na 3 das 4 a gente tem aulas para resolver os problemas do IPT. Então, eu acho isso maravilhoso. Tem alguém falando aí, ó.
Era eu, que na Unicamp é o curso integrado, graduação, mestrado e doutorado. Qualquer aluno da física ou de outras áreas pode se matricular. Inclusive, a nossa equipe ela tem diversidade de áreas também, não é só estudantes de física, tem estudantes de outras áreas que fazem parte da equipe. O Álvaro está aí mexendo a cabeça.
O Álvaro faz o quê, Álvaro?
Eu faço engenharia elétrica.
Ah, tá, maneiro.
Tá ali perto, tá ali perto.
Bom, eu não sei como é que tá o time de Harvard nessa competição, mas eu mandei para os meus professores aqui lá do departamento e o pessoal ficou interessado em participar também, achou bem legal o modelo e tal. Muito massa que é em inglês, porque eu posso mostrar para eles também, né?
Sim, pô.
Eu não vi nenhum time dos Estados Unidos, né, na competição do IPT. Tem algum?
Tem. Eles têm competição nacional também.
Entendi.
Ano passado, se eu não me engano, foi Cambridge. Foi. Não, foi.
Quando foi a primeira edição, tinha o cara que organizava me mandou um e-mail, eu falei assim, não vou defender a bandeira do Tio Sam hoje, não.
Aí sim, Roots.
Por sinal, a equipe dos Estados Unidos que foi, metade dela era brasileira.
Pior que foi mesmo. Isso aí eu descobri. Que o cara que chamava Matheus. Tô vendo o zap, Henrique. Tava tentando ser discreto, mas estou no zap.
Matheus estudou com a gente na USP e foi pra Rice depois.
Isso.
O
Matheus,
foi meu colega de lab. A gente fez lab 1 juntos.
Um traidor da pátria. Tô brincando.
Tem tanto Matheus aqui que eu tô perdido no... Eu não sei quem tá chamando. Quem.
Qual Matheus?
Caraca, pior que são 3 ou 4.
Você é um quinto Matheus.
Nossa. Mas aqui, ó, chegamos ao esperado momento. Nós temos já a... Henrique, fala alguma coisa aí. Você que tá aí mandando tudo. Vai, fala aí alguma coisa. Henrique, fala comigo. Ok.
Agora sim, acho que o pessoal do YouTube está me ouvindo. Te mandei aí o PPT, Matheus, se você puder confirmar e aí transmitir, porque se eu colocar para transmitir aqui, vai cair aqui. O PC não vai aguentar.
Não, sem problemas. Temos.
No
Estou vendo
passado
aqui.
a gente teve um problema com isso.
Não, sem problema. Já estão aqui. Estou terminando de checar os slides, vamos ver. Essas coisas são... Eu só arrumei um detalhezinho aqui. Mas a gente tem que ver também, Henrique, em que momento que a Débora gostaria de falar alguma coisa, né? Será que seria legal falar antes, assim, de tudo? A gente já começa falando com ela, você acha que seria legal?
Ela que...
O que você acha?
Professora Débora, se você quiser já falar, a senhora pode... Estamos aí ouvidos.
Eu só queria parabenizar aí pela organização. Eu fiquei só um pouquinho, mas fiquei super bem impressionada. Achei um negócio super legal, muito bem pensado. Fica o convite também para vocês escreverem uma notinha lá para o boletim da SBF, né? O ideal seria ter feito antes, para a gente poder divulgar a tempo de outras pessoas poderem acompanhar. O boletim é recebido aí por 15 mil pessoas semanalmente. Então, é um bom jeito da gente disseminar a informação, mas ainda pode acontecer. Se vocês mandarem uma notinha até quarta-feira, ainda sai na quinta, dizendo quais foram as equipes que participaram, qual é a dinâmica que não é bem uma disputa, né? É uma disputa, mas é uma disputa colaborativa. Achei muito legal a história do oponente, aí pergunta e depois pode acrescentar. Então, para uma outra releitura dos mesmos problemas, acho que as duas equipes que se enfrentam aí podem crescer e fazer coisas diferentes. É muito bom. Só queria deixar os parabéns para todo mundo que participou, para todo mundo que organizou e que essa coisa possa crescer, porque eu acho que é tudo de bom, né? Se as universidades todas tivessem disciplinas voltadas para esse tipo de coisa, as reclamações que eu ouço quanto a laboratórios de física básica, por exemplo, talvez fossem minimizadas, né? Eu ouço muitas críticas no Brasil dizendo, e é verdade, infelizmente, de que tem tantos físicos teóricos porque os laboratórios são mais do mesmo há 100 anos, né? Então, de repente, uma coisa nessa linha pudesse mudar a dinâmica de como as pessoas enxergam um pouquinho da física experimental e a correlação que isso tem com a parte teórica. É muito bom, parabéns, adorei.
Então tá.
Muito obrigado.
Obrigado.
Ficamos muito felizes. Matheus, tudo certo aí para
Tudo certo. Teve um errinho aqui que ainda bem que eu acertei, porque pai amado, ia ser interessante.
Ainda bem que você revisou, né?
Nossa senhora.
Pessoal,
mas tudo
é
bem.
um desafio fazer várias coisas ao mesmo tempo aqui. Pode parecer que eu não falo muito, mas eu tenho que ficar cuidando do YouTube. O Matheus fica me mandando mensagem toda hora. Mensagem pro relógio, mensagem pra outra sala. Chair da outra sala, relógio da outra sala. O streamer da outra sala que foi o professor Antônio, que ajudou bastante também. Então, tem bastante coisa aqui acontecendo no background, que é por trás aqui das coisas aqui.
Opa, peraí, deixa eu só ver aqui. Deixa eu fechar isso aqui, gente. O que é isso aqui? Isso aqui tá certo, né? Tá certo, arrumei. Então, beleza. Deixa eu ver aqui. Bom, agora preparei mais uma firulinha aqui, mas é rapidinho. Então vamos lá. Acho que a gente pode fazer em português, né?
Sim, acho que sim, podemos falar.
Não tem problema, já cansei de falar inglês, né? Não gosto de falar na língua dos outros. Tô brincando. Vamos ver aqui. Então tá. Senhoras e senhores, vocês que estão aí no YouTube acompanhando, ou que estão aí na sala, aguardando ansiosamente pelo desfecho do 4º Torneio Brasileiro dos Físicos, a seleção nacional para o IPT. Chegou a hora de saber quem vai representar o Brasil lá na Colômbia. Mas, claro, a gente vai falar um pouquinho antes das coisas no geral, né? A gente tem vários recadinhos para dar para vocês, né? Que eu acabei de lembrar agora, Henrique, que eu vou falar conforme a gente vai andando. Fecha aí, Matheus, eu quero almoçar. Né? Tem uma jurada aqui triste, a Bárbara. Tudo bem, Bárbara, vai ser rapidinho, não vai demorar não. Só contando um pouquinho assim do histórico, de novo, né, do IPT, a gente começou lá em 2016 formando uma equipe na UFBC, que a gente participou na Suécia do torneio, da equipe da fase mundial, né, porque ainda não tinha equipes do Brasil interessadas em participar. E em 2018 a gente voltou, né, a delegação do Brasil participou novamente do torneio internacional em Moscou, na Rússia, no Instituto de Física e Tecnologia de Moscou. Foi muito interessante, foi muito legal. Inclusive a gente conseguiu a medalha de bronze aí para o Brasil, né, e foi muito legal. E aí, voltando, né, tendo a vaga garantida, né, a gente formou, né, um comitê para para organizar um torneio nacional, porque a gente já tinha, né, o Brasil já tinha uma vaga garantida, então falamos, vamos competir, aí foi a primeira vez que a gente teve o BPT, então, né, e foi disputado entre a USP e a UFBC, a UFBC acabou ganhando naquela ocasião e indo representar o Brasil, então, no ano seguinte, 2019, lá na Suíça, na EPFL, e aí nós passamos aí, então, para o próximo ano. Aquele ano a gente não ganhou nenhuma medalha. Em dezembro de 2019 a gente realizou o segundo BPT, agora com 3 equipes, né, a Unicamp, a UFBC e a USP, e nesse campeonato, né, a Unicamp foi escolhida para representar o Brasil no internacional, mas aí por causa da pandemia teve várias coisas acontecendo, e o Brasil acabou não participando do campeonato mundial em termos de competição, né, competitivamente. E aí o que aconteceu então foi que o Brasil não teve essa participação, e aí a gente vai um pouco mais para frente, então, em abril de 2021 a gente teve o terceiro BPT, então, em que a Unicamp e a USP disputaram, e aí acabou que a Unicamp participou de novo e acabou sendo escolhido para representar o Brasil no Mundial. Aí, só que nesse caso o Mundial foi online em julho do ano passado, né, alguns meses aí atrás, e aí a Unicamp acabou, então, conseguindo ser a segunda colocada, né, foi um fight muito interessante, foi muito legal, e aí acabou ficando em segundo, então, a primeira medalha de prata, né, do Brasil na competição, e aí nós chegamos, então, depois disso, ao estado que a gente teve hoje, então, no quarto BPT, agora em fevereiro de 2022, com 4 equipes, né, muito competitivas, a UFMG, a Unicamp, a UFBC e a USP, tá? Foi uma competição muito legal, muito interessante, foi muito bom ter todos vocês aqui, nós temos até um print aqui que foi tirado de surpresa, claro, né, Henrique? Para que pedir para as pessoas, façam uma cara bonita? Não, só tira um print da tela, né? Enfim, foi muito legal, foi muito interessante a discussão com todos vocês, foi um momento, assim, muito feliz para todos, eu acredito, muito enriquecedor. E, claro, nós contamos também com a presença da Débora Menezes, que é a presidente da Sociedade Brasileira de Física, que é um negócio, assim, absurdo, nunca imaginei nos meus sonhos mais selvagens que teríamos, assim, poxa, uma pessoa tão importante, assim, no IPT, assim, participando, aí, né, enfim, gostando do que a gente faz e colocando a gente para frente, assim, abrindo portas até, né, como a Débora mesmo mencionou aqui durante essa conversa. Então, poxa, muitíssimo obrigado aí novamente pela presença da Débora, e esperamos então, né, que no futuro a gente tenha ainda mais equipes do IPT por todo o país, né, seria muito legal ter isso. Quer falar alguma coisa, Henrique? Eu que agradeço, ai que linda, a Débora é muito fofa, meu Deus do céu.
Não, a gente agradece todo mundo, a Débora, os jurados, né? Acho que se você passar no próximo slide aí tem as fotinhas.
Calma, claro, eu ia continuar aí os agradecimentos. Esse aqui é mais geral e para a Débora, que ela está ali, porque aqui nos próximos a gente tem uma foto só dela, mas esse ano nós contamos com jurados de vários diferentes lugares, né? Você quer falar alguma coisa disso aí, Henrique? Falar da diversidade? Como é que...
tivemos vários jurados de várias universidades, tentamos convidar universidades de fora, a gente teve um problema, mandamos muitos e-mails e poucos responderam, mas a gente fica feliz aí com o pessoal que topou o desafio de estar aqui, é cansativo, né? Dá trabalho, são 2 dias inteiros aí na frente do computador, mas nós queremos agradecer a todos os jurados que puderam colocar seu tempinho aí para julgar as equipes, dar feedback para as equipes e selecionar a melhor equipe do Brasil para o internacional agora na Colômbia, né? Então aqui é uma fotinho de todos os jurados e as universidades da onde eles vieram.
Isso aí, pô, muito obrigado a todos os jurados. Então, sem vocês, realmente não ia ter como fazer o torneio, então por isso que a gente agradece bastante mesmo. Temos também o staff, né, do BPT esse ano. Aí tem eu, né, o Matheus, mas eu já falo muito aqui, então eu falo o nome de todo mundo. Tem a Maria Carolina, tem o Gustavo Saraiva, né, o Henrique Ferreira, que está sempre aí também nas transmissões. Aí tem a Mariana Mercúrio, que ajudou a gente agora bastante, né, também a fazer uns slides, né, uns slides para a gente. Teve e ela também foi chair, né, de uma das sessões. A Melissa também, ajudou a gente, foi chair. A Maria Carolina também tinha sido chair. Então, muito legal ver aí também a participação delas, né? A Melissa também, inclusive, integrou a equipe da UFABC em 2019, assim como a própria Mariana já tinha participado da equipe da USP, né, das primeiras equipes da USP, e a Maria Carolina também da Unicamp, então, ex-participantes aí. Então, se você está pensando em se aposentar de PT, por favor, considere também ajudar a organizar o ano que vem. Esse é um apelo, né? Com um viés um pouquinho desesperado, talvez, né? Porque...
Exatamente. Acho que, pessoal, precisamos de ajuda aí. Precisamos de ajuda. É difícil de tocar um evento aí com poucas pessoas. Então, quem puder aí, quem tá na equipe aí, que vai sair da equipe, vai entrar no doutorado, tá acabando o mestrado, indo pro doutorado e quer ajudar, ano que vem, a gente está recebendo aí, tanto para fazer parte do staff da organização do ano que vem, quanto para fazer parte do comitê, né? Que eu acho que é os próximos slides aí.
Aí também temos, né? Vamos
tem que terminar de agradecer o Antônio, que foi, além de ser jurado, ele ajudou no streaming. Então ele fez o streaming de salas ontem à tarde e hoje de manhã. E o Tito, que também ajudou no streaming de uma das salas no primeiro horário. Faltou o Toneto. Nossa, eu peço desculpas, Toneto. Eu peço desculpas, Toneto, eu estava preparando esses slides durante a apresentação das outras equipes. Eu me senti um oponente ou um revisor, porque eu estava lá tentando fazer os slides enquanto mexia no YouTube e tentava responder, então foi bem difícil, mas faltou o Toneto. O Toneto fez os nossos Captain's Fights, ele está lá na Itália, né? Espero que esteja ouvindo a gente agora. Ele está lá na Itália fazendo seu doutorado em estrelas de nêutrons, inclusive foi uma das
diretamente de Itália.
Foi uma das perguntas dos Captain's Fights sobre estrela de nêutrons. E aí ele fez todos os Captain's Fights pra gente. Então, Toneto, muito obrigado aí. Desculpa não ter colocado.
Você não está nos slides, mas você está nos nossos corações.
Exatamente.
Olha só. Então é isso aí. Pronto, vamos. Então, temos mais agradecimentos também, né? E, só complementar, né? Do comitê. Fala aí do comitê, você que é o presidente, Henrique.
Então, pessoal, o comitê é formado por. A gente tenta formar por sempre um representante de cada universidade. Então eu peço aí para o pessoal da UFMG, pode ser um aluno e um professor, ou 2 professores da UFMG, participar do comitê. A ideia do comitê é ter esse canal de comunicação entre todas as universidades que são representadas, para a gente conseguir conversar sobre as regras do torneio, conversar sobre como é que a gente vai chamar jurados, né? Então, para decidir aí. Então, atualmente no comitê a gente tem os membros fundadores da UFABC, sou eu, o Matheus, o Ricardo, que esse ano não pôde ajudar a gente, mas nos outros anos ele ajudou bastante, né? O Ricardo Gitti, o Antônio, também está no comitê, foi uma das pessoas que ajudou muito, e aí a gente tem o Ricardo da USP, que infelizmente não pôde comparecer nesse BPT, o Leandro Tesler, o professor Pierre Louis, da Unicamp, o professor Hieron, temos o professor José Serbena também, da UFPR, que ele entrou no grupo ano passado, né? A Mariana Mercuti e o Lucas Maia, que também foi lá um dos membros que ajudou lá no primeiro BPT, né? E no segundo BPT. Então, a gente faz o convite aí para todos que foram jurados, todos que são membros de equipe que querem continuar de alguma forma. Estou indo para o doutorado, mas quero levar o BPT para outra universidade, né, para participar do comitê. Tá? Então, nós convidamos todos aí. Tá? Então, e fica também o convite para quem está nos ouvindo aí no YouTube, né, de preparar uma equipe para outra universidade. Se quiser, eu sou professor, estou vendo vocês falar aí, posso fazer parte do comitê? É super aberto, a gente tem um grupo no WhatsApp onde a gente conversa e troca ideia, então manda e-mail para a gente, né, ou comenta aí nos comentários do vídeo, a gente vai tentar responder e entrar em contato com você, para você vir fazer parte do comitê, vir representar a sua universidade aqui no Brazilian Physics Tournament. Eu continuo ou você fala, Matheus? Que a gente quer saber as notas, né? O pessoal vai enforcar a gente aqui. O pessoal deve estar louco querendo saber as notas, né?
Não, antes de falar das notas, eu queria falar um aspecto muito legal do torneio, que é uma coisa importante. Não, é sério. É sério. É que o Antônio, né, falou, né? O Antônio falou comigo aqui no chat, né? Ele me lembrou disso, que é importante. Se vocês trabalharam bastante os problemas, tá? Foi muito legal, foi muito interessante. Aí você pensa, mas aí acaba aí, eu fiz a minha pesquisa toda aí só para quê? É festa? Né? Eu não fiz por nada, eu só fiz e acabou. Não, aí, né, vai que não vou representar o Brasil, então, acabou a minha vida, então, e aí eu fiz todo esse trabalho para nada? Claro que não. Claro que não. Você é super encorajado a participar do IPT. E assim, porque o que é o IPT? O IPT não é só para você resolver uns probleminhas, né, e participar ou não da competição. É também para você publicar coisas, tá? Então aqui eu estou compartilhando a minha tela, tá? De uma revista própria do IPT, em que as pessoas, né, podem submeter trabalhos entendeu? Quando você é parte da comunidade do IPT. Então eu sei que eles são muito, eles aceitam, né, especialmente quando você fala que é do IPT, porque às vezes tem aquela questão de taxa e tal, mas eu acho que como a gente é do IPT, da comunidade, eles não cobram coisas, enfim, para submissão, mas o que a gente queria encorajar muito é que vocês continuem trabalhando nos problemas para poder, então, publicar eles também, certo? Porque, inclusive, o time do Brasil, né, em 2019, em 2017 e 2018, eu acho.
Foi um problema de 2017 que a gente publicou em 2018 e um problema de 2018 que a gente publicou em 2019. Né?
Isso, e aqui, ó, a gente tem vários problemas aqui, ó, por exemplo, esse aqui é o nosso, ó, do time do Brasil, que a gente conseguiu publicar um trabalho sobre um dos problemas do PT, que era muito legal também. Enfim, é bonito, entendeu? Fica legal você poder expor suas ideias, assim, em formato de artigo também, entendeu? Temos aqui até, por exemplo, do time da França. O time da França resolveu até o mesmo problema que a gente resolveu nesse ano, e aí tem aqui, enfim, eles conseguiram publicar também na revista. É muito legal porque você, ao submeter o seu trabalho, você também passa pelo processo de revisão e tal, que é algo que a gente tem que se acostumar bastante, né, na academia, né? Então é muito interessante isso também. Então esse aqui, por exemplo, é o trabalho da França. Enfim, nós temos a oportunidade de fazer isso, entendeu? Então até mesmo do ano passado, né, eu sei que alguns estudantes até da UFBC e da USP também estão aí se juntaram, né, para escrever sobre um dos trabalhos. Então é isso que a gente queria encorajar bastante vocês também, tá? Para a gente poder, enfim, conquistar o mundo, né? Imagina que legal se a gente, agora pensando alto, isso é um negócio que eu penso sempre. Se a gente aqui no Brasil forma, sei lá, não é um instituto, mas é tipo uma colaboração geral e que todos os participantes, sei lá, colaboram para escrever um trabalho sobre um dos problemas do PT, entendeu? Seria um negócio fantástico, um negócio absurdo, enfim, e eu acho que seria maneiríssimo. Enfim,
só uma coisa,
Matheus. A gente gostaria de encorajar também.
Para encorajar o seguinte, Matheus, porque a gente tem que perceber, a maior parte que já foi para fora, é lembrar que a física que o pessoal faz lá fora é a mesma que a gente faz aqui. A gente tem total condições de competir, inclusive em pesquisa, com qualquer lugar do mundo. Então, acreditar que a gente é capaz de fazer isso, tão bem quanto qualquer outro grupo de fora, e saber que a gente tem chances de uma maneira muito geral. Olha aí, segundo lugar, terceiro lugar, isso mostra que em pouco tempo o título de um torneio desse internacional vai aparecer no Jornal Nacional até.
Tomara. O dia que aparecer no Jornal Nacional, eu não vou fazer promessas aqui, porque eu sou meio doido com essas promessas, mas nossa, essa é uma doideira. Enfim, mas é isso que a gente queria encorajar, e também encorajar vocês, agora falando rapidinho, a submeterem problemas para o IPT também, tá? Porque todo ano o comitê executivo do IPT, eles recebem problemas que podem virar problemas do IPT, tá? Então, por exemplo, esse ano aquele da Sandy Fingertips foi proposto até pelo professor Ierum, da UFBC, né? E durante os últimos anos a gente tem tido vários problemas sugeridos por brasileiros que compõem a lista total dos problemas. Então, se você tem algum fenômeno interessante que você viu aí, e você fala, poxa, isso daria um bom problema do PT, submete, né, porque aí o Comitê Internacional vai decidir, né, se entra ou não na lista, e tem muita chance disso acontecer, tá? Teve ali, também, a Denise, uma colega nossa aí também, que já participou do YPT e tal, propôs um do pêndulo, por exemplo, desse ano também. Então, olha só, eu não sabia que dois dos problemas já tinham sido, dessa lista, são de brasileiros, muito legal. Eu tinha visto, enfim, nos outros anos, o do Sonic Black Hole, eu lembro que era um membro da equipe da UFPC, o André tinha submetido, ano passado teve o a questão do Branching Lights, que a Unicamp apresentou na final, que também foi submetida no brasileiro. Eu que submeti isso aí, eu vi na internet, achei legal, e falei, putz, isso vai dar um problema do IPT. Aí submeti, enfim. Então, tem essa curiosidade, e é muito legal. Tá bom, agora chega de falatório, tá? Vamos dar um resultado, porque eu também tô cansado. Não sem mais delongas, em quarto lugar, no Torneio Brasileiro dos Físicos. É legal nessa expressão, você passa o slide, você quer a resposta, mas você não tem. Enfim, em quarto lugar, nós temos o time da USP com 160,76 pontos. Parabéns aí, time da USP, pô, maneiro, obrigado pela participação. E olha só que desafio, né? Porque eles estão aí em 3 pessoas participando, tá? Então, assim, isso é uma doideira. Isso aí é fantástico, é muito legal. Parabéns aí pelo time da USP, pô, obrigado por terem participado. O USP tem participado aí com a gente, tem uns 4 anos já. Enfim, nossa, muito legal, cara. Então, se vocês até quiserem falar alguma coisa aí, se o capitão quiser falar alguma coisa, é só falar aí.
Agradeço muito.
Opa!
Agradeço muito a organização aí, também as outras equipes, estou bem feliz que a FMG se juntou. Esse campeonato foi muito legal pra gente, notar o desenvolvimento de cada membro da equipe, como a gente foi aprendendo com o caminho, isso foi muito bacana, assim. A gente agradece todo mundo aí, apesar das dificuldades, a gente se esforçou para estar aqui e participar desse final de semana super intenso com vocês aqui. Foi bom conhecer bastante gente. Valeu.
Pô, valeu então, Lauro. Obrigado aí por estar aí tanto tempo aí com a gente. Pô, eu lembro do Lauro. O Lauro ainda era uma criança da graduação.
No primeiro
Pois
BPT, a USP.
Desde aquele dia lá, eu vi o Lauro, falei, pô, caraca, o cara tá no primeiro ano, acho, da graduação, não sei o quê, e já tava, pô, sempre participando, foi muito legal, cara, então eu fico muito feliz aí de ver vocês sempre aí com a gente, pô. Tomara que ano que vem, pô, tem um time lá, completão, grande também, para poder, competir aí, cara, com, sei lá, de 6-6 mesmo, eu acho que foi até mais justo, até às vezes, o FAT, né? Porque em 3, nossa senhora, mas, pô, toda sorte aí, se precisando de qualquer coisa aí, de qualquer animação aí pra galera da USP, só fala com a gente que a gente tenta promover mais o torneio lá também. Então tá, vamos aí pro próximo. Opa, cadê o slide, gente? Em terceiro lugar, 3 pontinhos. Eu não sei se cada vez que eu abro o chat a transmissão fica zoada, espero que não. Vou parar de abrir o chat. Então, em terceiro lugar, do Torneio Internacional dos Físicos da etapa brasileira, nós temos conquistando medalha de prata. Na verdade é de bronze, erramos. Não é de prata. Essa aí é uma piadinha que o Henrique fez, tá? Então, gente, se vocês não gostaram, reclamem com ele. É o time da UFABC com 193,14 bronze, conquistando aí, então, a medalha de bronze. Parabéns aí ao time da UFABC. O time da UFABC que tá aí desde os primórdios do IPT, participando da competição, pô. Parabéns aí para vocês. Foi muito legal ver, enfim, a apresentação final da UFABC, eu, sinceramente, eu achei um absurdo, achei louquíssima. Gostei muito daquele blender ali, eu já até vi ali como baixar, porque eu quero usar, né? Não sabia nem que ele existia, mas aí vi, pô, imagina isso, você pegar os seus dados experimentais e conseguir fazer um negócio que, enfim, um absurdo, é o tipo de coisa que eu amo fazer, né? E, enfim, parabéns aí, pô, o capitão aí, alguém quer falar alguma coisa aí da UFABC? Pode falar aí, Rodrigo, se não quiser ficar triste, bolado.
Eu queria falar que eu fui o capitão esse ano, mas o capitão de facto, né, o real capitão da equipe é o Rodrigo. Rodrigo é nosso veterano, nosso titã, nosso gigante que a gente se apoia nas costas, entendeu? E nos ombros, né? E eu queria que o Rodrigo desse um discursinho aí de saideira dele, porque ele tá no overtime.
Que isso, que honra, pô.
Discurso!
Bom, muito obrigado então, gente. Muito feliz de pegar esse terceiro lugar aqui. A nossa equipe, ela sofreu por problemas aí, que eu imagino que, enfim, a USP e outras pessoas aí, outros grupos que talvez tivessem com intenção de participar no IPT também sofreram, com uma falta enorme de gente. E a intenção mesmo pro time da UFBC esse ano era manter a chama viva, né? Porque eu tô saindo ano que vem já, e o medo era que comigo saindo e sem participar do BPT, a gente ia deixar de ter um time na UFBC. Então foi importante manter, para segurar essa tradição aí que o Matheus e o Henrique começaram, né? Então é uma honra estar aqui segurando essa tocha, né? Muito obrigado, gente.
Isso aí, pô. Vamos ver. Ano que vem aí o pessoal já tá pegando uma experiência, né? Ver que tem caras novos. Fico muito feliz também de ver aí o pessoal novo no time. E é isso, pô. Mandaram muito bem. Eu achei um absurdo. O último apresentação lá eu gostei, nossa, pra caramba. Parabéns, mesmo. Enfim, eu gostei de várias, né? De todo mundo. Das gotinhas também, caindo na areia, enfim, um absurdo. Vamos ver aqui. Então, agora vamos para o segundo lugar. A parte chata, né, de revelar o segundo colocado, é que a gente sabe quem ganhou depois, né? Então, enfim. Mas, eu não sei nem como falar isso, que é tanta emoção. Henrique, você quer falar alguma coisa, Henrique, antes de revelar o resultado final?
Eu não sei o que tem no próximo slide. Eu não faço ideia do que tem no próximo slide.
Pô, pelo amor de Deus, cara. Eu já fui, enfim. Eu tô vendo, eu vou apresentar mais rápido, porque eu tenho medo das pessoas ficarem bravas comigo depois. Então, deixa eu ver aqui. Antes de tudo, calma, claro, né? Tudo sempre tem um antes, né? Nós, uma palavrinha dos nossos patrocinadores, então, porque aqui a gente trouxe uma pessoa muito especial que está aí com a gente, né, que está patrocinando a gente, que é, na verdade, ninguém, né? Não temos patrocinadores, então, por favor, se você está aí no YouTube, você falou, poxa, eu quero ajudar, eu quero, sei lá, pagar um coffee break, gente. Pagar um coffee break pra gente já seria uma coisa absurda. Tivemos o coffee break lá em 2017 na UFBC, proporcionado pela faculdade, foi, assim, um escândalo, entendeu? Foi muito bom, tinha empadão, tinha iogurte, tinha coxinha. O pessoal da USP lembra, né? O pessoal da USP comeu bastante esse
melhor coffee break que eu já participei na minha vida.
Olha o feedback.
Às vezes eu começava a terminar, você olhava para um lado, piscava, já voltou tudo pro lugar. Impressionante, muito bom.
Era a comida, assim, era uma velocidade, nossa, enfim. E aí, não à toa, a gente conseguiu unir, sei lá, 40 pessoas lá assistindo a uma competição de física, né? Foi muito bom. Então aí você que está aí de casa, quer patrocinar a gente, enfim, vamos ver. Oh meu Deus, pessoas me criticando pelo suspense, tudo bem. Vou rápido, porque a sociedade é a presidente da Sociedade Brasileira de Física, né? Vai que eu perco o meu título. Então, vamos continuar. Vamos lá, deixa eu ver aqui. Opa, cadê? Opa, deixa eu passar aqui pro próximo. Você tá ficando nervosa. Oh, meu Deus, não vamos deixar ela nervosa. Então tá. Então agora, gente, agora é isso. Acabou o suspense. Não tem mais suspense. Não vai ter mais suspense. Então, a segunda colocada do quarto torneio brasileiro dos físicos é a equipe... Ai. Eu esqueço quantos slides eu pus antes de revelar o negócio, aí eu me perco. Mas, então tá. A segunda equipe do Torneio Brasileiro dos Físicos é a UFMG, com 196,06 pontos na primeira participação deles no Campeonato Nacional. A gente está muito feliz porque vocês conseguiram ficar em segundo lugar já na primeira participação de vocês contra equipes tão experientes assim, de outros lugares, né, da UFBC, da USP, da Unicamp. Vocês conseguiram chegar em segundo lugar. E claro, a Unicamp esse ano conquistou novamente a vaga para representar o Brasil no campeonato que vai acontecer na Colômbia, do IPT, em Bucaramanga, na Colômbia, em maio. Tá? Então aí, primeiro assim, enfim, Eu esperava ouvir gritos, né, de felicidade. Podem gritar na chamada, pessoal.
Nossa, eu tô muito feliz.
Isso.
Você causou muitos problemas de coração nas pessoas.
Parabéns, pessoal da FMG.
Muito
Opa!
Parabéns, gente. Muito obrigado pela competição.
Que maravilha, pô. Enfim, se alguém quiser falar alguma coisa aí, compartilhar a alegria de vocês, pode falar.
Ai, nossa, sério, eu quero. Nossa, calma, tô tremendo aqui, gente. Sério, eu tô muito feliz com o resultado. Nossa, foi uma experiência incrível que a gente teve aqui. Nós conhecemos pessoas incríveis também. Nossa, eu tô muito feliz. Pessoal da Unicamp, USP, o FBC. Gente, sério, foi fenomenal esse evento. Eu não sei o que mais falar, porque minha cabeça literalmente parou de funcionar. Faz dias que eu não durmo. Eu acho que tá todo mundo sem dormir também. Tipo. É isso, eu vou colapsar daqui a pouco. Gente, alguém quer falar alguma coisa, por favor?
Que eu achei que, tipo, o resultado, a gente tá muito feliz com o resultado, porque a gente teve muita dificuldade desde o início, assim, a gente, desde falta de tempo, de falta de não ter experiência para saber como é que seria a organização entre a gente, de não saber mesmo como é que seria o torneio, enfim. Que a gente começou depois atrasado por causa do início do semestre. Então, tipo, ter chegado no segundo lugar foi muito bom mesmo. E é isso, eu tenho que agradecer a todo mundo. E foi incrível fazer parte disso com vocês, com a minha equipe, que eu adorei, tipo, fazer isso com vocês, com os jurados, com a equipe das outras universidades. E é isso, gente. Obrigada.
Meu Deus, que alegria.
Mano,
Felicidade,
vocês
hein?
destruíram, desculpa, eu tô muito feliz, vocês destruíram, sério, puta merda.
Sério, a gente tá muito feliz.
Tá ao vivo, Lucas?
Nossa,
ao vivo!
Tem gravado pra eternidade.
Posso dar um parabéns especial para a FMG também? Porque eu formei lá, né? Fiz graduação, mestrado, doutorado, tudo lá na FMG. Sou criado a pão de queijo da cantina de Sex, então sempre também teve um lugar no meu coração, né? Quando o Bira e a Carol falaram, não, a gente vai montar uma equipe, eu falei, pô, sensacional. Aí eu vi, parece que o Elmo empolgou também, assim, bom, mandem um abraço para todo mundo, estou muito feliz, parabéns pela participação e ano que vem promete.
Nossa, é isso.
Tem o dobro de participantes.
Pode falar.
O pessoal da Unicamp também, quiser comemorar, pode comemorar aí, abrir uma cerveja.
Tem um monte mutado. Meus pais vieram aqui também gritar no ouvido aqui.
E cadê os pais ali do Leonardo? Olha lá, ao vivo!
Olha, tá chamando vocês aqui, ó.
Olha lá, o tchauzinho, rapaz! Opa! Aí sim!
Valeu! Fala que nós vamos patrocinar o próximo.
Ó, ele tá falando que
nós
vamos
vamos dar uma
patrocinar
força.
aqui, ó.
O coffee break é para mostrar conta.
Opa! Tranquilamente, hein, ó. Promessa é dívida. Isso aqui tá sendo gravado, hein, pessoal? Todos estão vendo aí.
Tá sendo gravado. Mas muito obrigado à organização, vocês arrasaram demais. E todas as equipes, foi muito legal. Todos os fights. Eu acho que o mais legal do PT é que você sai aprendendo. Cada fight você aprende mais e você sempre ganha alguma coisa. Valeu demais todo mundo. Acho que é isso. A gente está muito feliz, acho que... enfim, valeu para todo mundo mesmo. E parabéns para a FMG também, principalmente, que na primeira participação mandaram muito bem também. E é isso.
Sim.
Eu também vou aproveitar o comentário do Léo. Embora eu estude agora na Unicamp, eu sou mineiro, eu sou de Minas, e eu também já participei do YPT, então eu sei, assim, existe um paralelo muito grande que eu já experimentei de assim, participar da primeira vez e assim, de certa forma, a gente é um outsider, né? A gente vem para essa competição, assim, sem muito conhecimento e assim, chegar com a cara e a coragem do jeito que vocês fizeram e sair com um resultado tão bom desses, tão bom que nem esse, é um negócio, assim, que vocês devem comemorar muito. É surreal o que vocês fizeram. Parabéns. E obrigado, né, por representar o Estado.
Também quero parabenizar todo mundo. Foi tão sensacional. discutir os problemas de física, fazer os experimentos, passar a noite sem dormir fazendo slide. Competição muito, muito legal. Eu também, como Álvaro, no ensino médio, cheguei a participar do São PT, então só reforçar o que ele falou, porque achei muito legal a postura da FMG. Eu espero que cada vez mais a gente tenha mais universidades na competição, que nem a gente vê no São PT, tem 20 a 30 colégios no torneio. E eu espero que vá crescendo com o tempo e que todos nós vamos aprender física juntos. E muito incrível também. Obrigado a todo mundo de coração.
Eu queria mandar um abraço pro pessoal de Brasília. Eu, assim como o Álvaro, não sou do estado de São Paulo, sou de Brasília. E eu estou tentando motivar o pessoal da UNB para participar da competição. A Carol também é do mesmo colégio que eu, inclusive. E lá tem muito potencial, só convencer o povo. Mas eu acho que agora com esse resultado eles vão me dar mais moral.
Ai. Vidão, hein, gente? Eita, maravilha. Olha, ó, o professor Antônio é formado da UNB, hein? Que era júri também aí. O Antônio Neves. Ai. Mas é isso, gente. Poxa, muitíssimo obrigado aí por tudo. Essa sim é uma foto direitinho aí, todo mundo sorrindo, todo mundo feliz.
De onde veio essa foto?
Tem surpresas. Então, essa aí ficou, boa, né? Mas é isso, pô. Eu queria agradecer a todo mundo, então, por ter participado do BPT. Foram muitas horas aí, muita preparação de todo mundo, né? Então, obrigado pelo tempo que vocês se dedicaram a essa competição. E, assim, eu garanto que vocês nunca vão perder nada do que vocês se dedicaram, entendeu? Vocês sempre só vão crescer mais e mais. E, enfim, o IPT é uma coisa muito única, né? Para mim, pelo menos, é uma coisa muito especial. Enfim, eu fico muito feliz que para vocês também seja aí um grande sonho, uma grande alegria, enfim, que vocês continuem aí participando mais e mais anos também. E é isso, gente. Acho que agora, Henrique, quer falar mais uma coisa? Já vai encerrar
acho que todo mundo já agradeceu tantas vezes, né? Então, agradecer o pessoal que está aí no YouTube e acho que agradecer todo mundo que está na sala, todos os jurados, professores, organização e equipes por esse excelente final de semana de discussão de física. E falar, pessoal, importante vir fazer parte do comitê, a gente precisa de pessoas para organizar ano que vem, hein? Ano que vem a gente vai precisar já eleger um próximo presidente aí, então estou torcendo aí para pessoas como a Mariana, a Maria Carolina, que já ajudaram na organização aí, tentem assumir essas posições aí, né, e outras pessoas assumam aí, a gente ciclando a organização também, né, para, como o Rodrigo falou, a chama do IPT não morrer, né, não só em cada universidade, mas também aqui na organização, né, e no pessoal aqui do BPT. Precisamos de mãos aqui nos ajudando, tá? Pessoal do YouTube também, se tiver aí numa outra universidade quiser vir fazer parte aí, nós estamos abertos aí.
Então é isso, pessoal. Pô, muito obrigado aí. Boa noite, bons sonhos, como diria a Débora. Enfim, obrigado por tudo. Obrigado por...
Que foi? Não, eu ia falar que Unicamp, a gente espera aí um excelente resultado da Colômbia, hein? Vamos lá. Quem sabe essa vez não vem aí o primeiro troféu, né? A primeira medalha de ouro, hein? Porque a gente tá batendo na porta e tá chegando bem perto, hein? Então eu tô torcendo aí pra Unicamp aí pegar trazer esse caneco pro Brasil, hein? Esse ano, daqui.
Tomara. E a gente espera que as outras equipes possam ajudar a gente também, viu? Pode enviar os seus problemas, vamos discutir. Vamos tentar fazer o melhor pro Brasil aí, pra gente ir bem nessa competição.
Não, vocês têm que destruir agora,
com certeza,
mano.
Agora é todo mundo ajudando o Unicamp
Parabéns,
pra
viu?
gente trazer o ouro pro Brasil.
Queremos fazer um
podia
bom
combinar
trabalho que vocês todos fizeram.
vocês mandam pra gente que vocês têm os problemas resolvidos, que vocês já têm, que vocês já desenvolveram, e aí a gente manda pra vocês, tipo, todo mundo junto e, né, ver se sai alguma coisa.
Isso aí.
Pessoal,
isso aí.
Vou encerrando a transmissão aqui no YouTube, então. Boa noite a todos aí. Vocês
Boa noite.
que estão aqui na sala, se quiserem ficar mais um pouco, mas no YouTube eu estou encerrando aqui. Tchau, pessoal.
Beleza. Tchau.
Tchau,
Até
gente.
mais.
Boa noite.
Tchau, gente. Parabéns.
Tchau, pessoal.
Tchau, pessoal.
Tchau, muito obrigado a todo mundo.
Só que queria falar.